Dari yang kecil hingga yang besar, memberi hadiah sudah jadi bagian dari kebiasaan kita. Tapi, bagaimana dengan uang terima kasih, uang pelicin, atau bahkan uang damai? Apakah itu kebiasaan yang benar? Padahal, apapun yang kita berikan pada penyelenggara negara dan pegawai negeri itu termasuk gratifikasi loh. Gratifikasi yang sifatnya netral bisa berubah jadi ilegal kalau ada konflik kepentingan di baliknya. Seperti uang terima kasih, uang pelicin, dan uang damai tadi. Apa yang bisa kita lakukan agar kebiasaan buruk ini berhenti? Salah satunya adalah dengan membangun budaya anti gratifikasi. Budaya anti gratifikasi adalah suatu cara hidup di masyarakat untuk tidak memberi dan menerima gratifikasi yang berhubungan dengan jabatan dan bertentangan dengan tugas atau kewajiban pegawai negeri atau penyelenggara negara. Tentunya, mewujudkan budaya anti gratifikasi ini tidak lepas dari peran penting 5 komponen berikut, yang terdiri dari penyelenggara negara dan pegawai negeri yang memahami serta patuh terhadap aturan gratifikasi. Juga lembaga pemerintah yang berfungsi untuk membangun lingkungan yang bebas dan bersih dari gratifikasi. Dibantu partisipasi masyarakat luas untuk berhenti memberi gratifikasi kepada penyelenggara negara atau pegawai negeri. Serta dukungan swasta untuk melakukan praktik bisnis yang bersih dari gratifikasi, suap, dan uang pelicin. Ditambah dengan organisasi masyarakat sipil untuk mengawasi pelaksanaan pelayanan publik. Membangun budaya anti gratifikasi bisa dimulai dari hal kecil, seperti menolak jika ada upaya pemberian dengan maksud mencurigakan. Ayo, mulai dari diri sendiri, jadikan perilaku anti gratifikasi kebiasaan kita. Untuk melaporkan gratifikasi, klik goal.kpk.go.id. Klik kpk.go.id/gratifikasi untuk info lengkap soal gratifikasi. Dari yang kecil hingga yang besar, memberi hadiah sudah jadi bagian dari kebiasaan kita. Tapi, bagaimana dengan uang terima kasih, uang pelicin, atau bahkan uang damai? Apakah itu kebiasaan yang benar? Padahal, apapun yang kita berikan pada penyelenggara negara dan pegawai negeri itu termasuk gratifikasi loh. Gratifikasi yang sifatnya netral bisa berubah jadi ilegal kalau ada konflik kepentingan di baliknya. Seperti uang terima kasih, uang pelicin, dan uang damai tadi. Apa yang bisa kita lakukan agar kebiasaan buruk ini berhenti? Salah satunya adalah dengan membangun budaya anti gratifikasi. Budaya anti gratifikasi adalah suatu cara hidup di masyarakat untuk tidak memberi dan menerima gratifikasi yang berhubungan dengan jabatan dan bertentangan dengan tugas atau kewajiban pegawai negeri atau penyelenggara negara. Tentunya, mewujudkan budaya anti gratifikasi ini tidak lepas dari peran penting 5 komponen berikut, yang terdiri dari penyelenggara negara dan pegawai negeri yang memahami serta patuh terhadap aturan gratifikasi. Juga lembaga pemerintah yang berfungsi untuk membangun lingkungan yang bebas dan bersih dari gratifikasi. Dibantu partisipasi masyarakat luas untuk berhenti memberi gratifikasi kepada penyelenggara negara atau pegawai negeri. Serta dukungan swasta untuk melakukan praktik bisnis yang bersih dari gratifikasi, suap, dan uang pelicin. Ditambah dengan organisasi masyarakat sipil untuk mengawasi pelaksanaan pelayanan publik. Membangun budaya anti gratifikasi bisa dimulai dari hal kecil, seperti menolak jika ada upaya pemberian dengan maksud mencurigakan. Ayo, mulai dari diri sendiri, jadikan perilaku anti gratifikasi kebiasaan kita. Untuk melaporkan gratifikasi, klik goal.kpk.go.id. Klik kpk.go.id/gratifikasi untuk info lengkap soal gratifikasi.
Bismillahirrahmanirrahim. Honorable participants, perwakilan dari kementerian dan lembaga, para pejabat tinggi pratama, pejabat administrator, dan kepala balai di lingkungan Direktorat Jenderal Cipta Karya, Direktorat Jenderal Bina Konstruksi, Direktorat Jenderal Bina Marga, Direktorat Jenderal Sumber Daya Air, dan Direktorat Jenderal Prasarana Strategis. Para kepala dinas, pengampu penyelenggaraan bangunan gedung, pemerintah daerah provinsi, dan kabupaten atau kota di seluruh Indonesia. Para sivitas akademik dan ketua asosiasi profesi. Para penyedia jasa bidang konstruksi, para narasumber, dan moderator. Secara khusus perwakilan Japan Society of Seismic Isolation, mitra kolaborasi kami dalam penyelenggaraan workshop ini. Distinguished representatives from JSSI. We sincerely appreciate your presence and valuable collaboration. It is an honor to have you here with us today as our speakers. Serta Bapak Ibu peserta workshop sekalian. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. Shalom, Om Swastiastu, Namo Buddhaya, salam kebajikan. First of all, let us praise the presence of God Almighty, who has given guidance, happiness, health, and grace, so that we can attend and participate in this event without any obstacles. At this special occasion, we thank for the time given to us. We appreciate to all participants who join this event, and we are sure that we will get benefit in joining this activity. Welcome to workshop on seismic isolation in practice, called Retrofit Solutions and Innovative Structures, in collaboration with Japan Society of Seismic Isolation. Distinguished participants, let me deliver the structure of the event today as follows. The first agenda is remarks and opening by Head of Sub-Directorate of Building and Environmental Infrastructure Reliability. The second agenda is speech by representative of JSSI. The third agenda is workshop by the speakers. and the last is closing. Now, we start in the first agenda, remarks and opening by Head of Subdirectorate of Building and Environmental Infrastructure Reliability, Mr. Ferry Eka Putra, STMDM. The time is yours.
Ya, Bismillahirrahmanirrahim. Hari ini Bapak Direktur tidak bisa hadir secara langsung, jadi mohon izin saya menyampaikan sambutan dari beliau. I'm sorry, our director cannot attend this meeting today, so he asked me to deliver his speech, and I will deliver the speech in bahasa. Yang kami hormati Ibu Bapak para undangan dari perwakilan kementerian dan lembaga, para pejabat tinggi Pratama dan pejabat administrator dan kepala balai di lingkungan Kementerian Pekerjaan Umum, para kepala dinas pengampu penyelenggaraan bangunan gedung, pemerintah daerah, provinsi, kota, dan kabupaten di seluruh Indonesia, para sivitas akademi, dan ketua asosiasi profesi, para penyedia jasa di bidang konstruksi, baik dari konsultan, kontraktor, maupun MK, para narasumber dan moderator, secara khusus perwakilan dari Japan Society of Seismic Isolation, di mana kegiatan hari ini merupakan hasil kerjasama antara Kementerian PU dengan JSSI. Distinguished representative from JSSI, we sincerely appreciate your presence and valuable collaboration. It's an honor to have you to have us with us today as our speakers. Ibu Bapak, para peserta workshop sekalian, Assalamualaikum warahmatullahi wabarakatuh. Good morning everyone. Pertama-tama marilah kita bersama memanjatkan puji dan syukur kehadirat Allah SWT atas karunia dan hidayahnya, sehingga kita bisa mengikuti acara workshop on seismic isolation in practice, codes, Retrofit Solution and Innovation Structures, yang merupakan tadi saya sampaikan kerjasama dengan Japan Society of Seismic Isolation, dan semua insya Allah dalam keadaan sehat. Ibu Bapak peserta workshop yang berbahagia, Indonesia merupakan salah satu negara dengan tingkat risiko kegempaan yang tinggi, sehingga sebagai konsekuensinya dari lokasi geografis yang berada di pertemuan beberapa lempeng tektonik. Dalam beberapa tahun terakhir, berbagai peristiwa gempa bumi yang terjadi di tanah air telah memberikan pembelajaran berharga bagi kita akan pentingnya peningkatan dan inovasi dalam bidang rekayasa struktur. Upaya mitigasi bencana melalui penguatan sistem konstruksi menjadi suatu keharusan guna meminimalkan risiko kerusakan bangunan serta melindungi keselamatan masyarakat. Seiring dengan perkembangan ilmu dan teknologi, seismic isolation atau isolasi seismik, dalam SNI kita menyebutnya isolasi seismik, telah menjadi salah satu pendekatan yang terbukti efektif dalam meningkatkan kinerja bangunan terhadap gempa, dengan cara mengurangi percepatan gempa yang diteruskan dari tanah ke struktur. Teknologi ini memberikan berbagai keunggulan seperti peningkatan keselamatan penghuni, perlindungan aset, pengurangan biaya pemulihan pasca gempa, dan memungkinkan bangunan tetap operasional setelah terjadinya gempa. Oleh karena itu banyak bangunan-bangunan di negara maju, ya khususnya di bangunan rumah sakit, itu sudah banyak menggunakan teknologi based isolation ini. Pada kesempatan berbahagia ini kita berkesempatan untuk mendengarkan sharing knowledge dari Japan Society of Seismic Isolation yang akan memaparkan contoh-contoh penerapan teknologi isolasi seismik yang ada di Jepang. Dan mereka telah mengembangkan dan menerapkan teknologi ini secara konsisten dalam berbagai tipe bangunan selama beberapa dekade ke belakang. Kita juga akan mendengarkan pemaparan dari para narasumber dalam negeri terkait dengan perkembangan ketentuan desain seismik isolasi ya, yang telah diatur dalam SNI 1726 tahun 2019. Serta juga ada perwakilan nanti dari industri nasional yang juga mendorong penggunaan base isolation dan mereka akan menyampaikan pengalaman dan pengembangan yang telah mereka lakukan sebagian dari upaya untuk mendorong kemandirian teknologi, serta peningkatan kapasitas penerapan isolasi seismik di Indonesia. Melalui rangkaian materi dalam workshop ini, semoga dapat membuka wawasan kita bersama dalam mengaplikasikan, mengembangkan, dan melakukan inovasi terkait dengan teknologi seismic isolasi pada pembangunan baru maupun retrofitting di bangunan gedung di Indonesia, termasuk dalam upaya untuk penyusunan dan penyempurnaan standar nasional Indonesia kita di bidang ketahanan gempa. Jadi Ibu Bapak, saya harapkan manfaatkan hari ini, momen ini untuk sharing, bertukar informasi dan mendapatkan banyak pengetahuan dari rekan-rekan kita dari JSSI. Ibu Bapak yang saya hormati, demikian yang dapat kami sampaikan. Akhir kata dengan mengucapkan Bismillahirrahmanirrahim. Acara workshop on seismic isolation in practice, codes, retrofit solution and innovation structures yang merupakan kerjasama antara Kementerian PU dengan Japan Society of Seismic Isolation secara resmi dibuka. Semoga pelaksanaan acara hari ini dapat berjalan dengan lancar dan kita semua mendapatkan manfaat yang maksimal. Sebagai penutup, kami mengucapkan terima kasih atas kesediaan waktu dan pemikiran Ibu Bapak dalam acara hari ini. Thank you again to JSSI for your presence and contribution. We wish you pleasant stay in Indonesia. Dengan ridha Allah Subhanahu wa taala, semoga cita kita bersama dapat terwujud bersama. Amin ya rabbal alamin. Demikian sambutan dari Pak Direktur Bina Teknik Bangunan Gedung dan Penyataan Lingkungan. Selamat menikmati acara workshop hari ini. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Step on to the following agenda is speech by representative of JSSI, which will be delivered by Professor Taiki Saito from Toyohashi University of Technology. The time is yours.
Good morning. Good morning. Good morning. My name is Taiki Saito. I'm a leader of Japanese team of Japan Society of Seismic Isolation. I would like to express our gratitude to the staff of Ministry of Public Works in Indonesia to organize this workshop. This program is started 10 years ago, supported by Japanese Ministry of Land Infrastructure and Transport to disseminate Japanese technology around the world. And actually, 2017, we came here in Indonesia to organize the workshop. So this is the second time. And yesterday, we visited one base isolation building in Jakarta and one factory which produce isolation device. So I was surprised the progress of Indonesia about this seismic isolation technology. So Japan and Indonesia have common problems of natural disasters, earthquake, flood, typhoon. And before coming to Indonesia, in Japan, we watched the news about severe flood in Indonesia. So we'd like to express our deepest condolences with people who suffered by this flood. So this workshop is about seismic isolation technologies, which protect not only building, but people inside against earthquake. So I hope this workshop is productive and our cooperation will continue in the future. Thank you very much.
The next agenda is workshop by speakers. This agenda will be led by our moderator, Dr. Eng Rudi Setiaji Agustini Tias. The time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Thank you for the MC, Mrs. Awa. Ladies and gentlemen, right now we are going to enter the main session. This session will be moderated by me, Rudi Setiaji, and today we have three excellent speakers from Japan that will present and give their experience and their knowledge and sharing to us today. They are first, I will invite the first one is Professor Taiki Saito. Please come and join me on the stage. And then the second one is Mr. Akit Sugu Muramatsu. Muramatsu-san, please join me on the stage. And the third one is Mr. Yusuke Hota. Hota-san, come and join us on the stage. Oh, sharing not on. Oke. Mohon panitia untuk bisa memberikan izin sharing Zoom kepada Pak Saito. Namanya. Yang pakai huruf Jepang di accept semua aja. Okay, we have all the three speakers on the stage, and first we will have the presentation one by one. So I need to all participants to keep their question first, and then we can have a discussion session after each of the presentation. So first speakers, I will introduce first. The first one is Professor Taiki Saito. Welcome, Professor. Saito Sensei is a professor from Department of Architecture and Civil Engineering of Toyohashi University of Technology. He obtained his latest degree, Doctor of Engineering, from Tohoku University of Japan. Today, he will present about the effort toward international harmonization of seismic isolation design code. So, Professor Taiki Saito, please be welcome to present.
Can you hear me? Okay. Okay, I would like to start my presentation. So in the beginning, I would like to introduce about JSSI, Japan Society of Seismic Isolation. And because the success of seismic isolation technology in Japan, depending on deep contribution of JSSI. You can visit the website of JSSI from the website you can see here. There's an English website. JSSI was established almost 30 years ago. Right now, we have a class 1 regular member. It is a corporate member, 87. Class 2 is individual member. We have 232. And supporting members, it is a kind of a governmental organization, and 111. Under the president of JSSI, there are many steering committees: Committee of Technology, Committee of Real Scale Testing, Committee of Dissemination, Committee of Foreign Affairs. I am a chairman of this committee, I don't know, more than 10 years, maybe nearly 20 years. Committee of Maintenance, Committee of Qualification System, Committee of Nuclear Facility, Committee of Commentation. JCSI also worked for like evaluation organization on behalf of government. So evaluation committee for structure, evaluation committee for devices. So after checking by this evaluation committee, we put some stamp of government on behalf of government. And the JCSI publish mention journal every 3 months. It contains introduction of new seismically isolated buildings, report of symposium, site visit, report of committee activity, short essay. So it is very important source of information. You will get recent latest achievement of seismically isolated buildings in Japan. And this journal is available on the website. We issue electric book version. So we welcome people in Indonesia who becomes a member of JCSI so that you can obtain this journal online. However, all language is in Japanese. I'm sorry. But you can use the translator, right? So I will show you the current development of history of development of isolated buildings. This is the number of annual number of buildings of isolated buildings. When JCSI was established 30 years ago, very few number of isolated buildings. People don't believe isolated buildings. They don't know anything else. However, when Kobe earthquake happened in 1995, there were 2 buildings in Kobe, seismically isolated, and no damage at all. And people started realizing, oh, isolated technology, really good. So the number of isolated buildings suddenly increasing. Also, after Tohoku earthquake 2011, again, people realized the excellent performance of seismically isolated buildings. So suddenly the number is increasing. However, after spending time, people forget about the earthquake and the number is decreasing. Also, there is isolated houses. Usually we adopt sliding techniques. So we separate building and isolated houses. We call detached houses. Anyway, the number is very low, almost 0. However, even after Kobe, the number doesn't increase. Because if you adapt isolation technology, it requires special evaluation and cost money and takes time. So it is not adapted for private houses. Then, year 2000, government issued simplified calculation method. So adapting this simplified method, the process of regulation is shortened and streamlined the process. Suddenly, the number of detached houses increasing. And at Tohoku earthquake, however, after Tohoku earthquake, the number is declining again. Because there were excessive deformation at this Tohoku earthquake, and some isolated houses go over the limitation. So now, company try to countermeasure how to improve the performance. So I believe in the future the number will increase again. Okay. Also, there are buildings retrofitting existing building to be isolated buildings. The number increased after Kobe, also after Tohoku earthquake. But as you can see here, the number itself is less than 20. So not so many, because it costs money to retrofit existing building. And it is limited to very important building like a museum or government offices. This graph shows a building usage of which adapt to isolated buildings. More than 30% is a condominium, and 50% is office building. Government or hospital is 12 and 9%. For example, in Turkey, there is a regulation. Big hospital must be isolated. So hospital is number one in Turkey. Or China, also there is a regulation in Yunnan province, for example, government order school or hospital should be isolated. So school and hospital is dominant. But in Japan, we don't have such regulation. Why condominium is number one? Because Japanese people concerned about earthquake safety very much. So if you build a condominium with isolated techniques, people notice, oh, this building is safer. We buy this condominium, even it's expensive. So this is Japanese, how to say, people thinking. This is a device adapted for seismically isolated building. So natural rubber bearing, lead rubber bearing, and high damping rubber bearing. This rubber bearing is very dominant, almost 75%. And sliding device or close curved surface slider, yes, it's getting popular, especially curved surface slider. Yesterday, we visited one building in Jakarta which adapted curved surface slider or friction pendulum slider. But in Japan, rubber bearing is very, very popular. So you may think seismically isolated building is popular in Japan, but actually, I don't think so. Because in Japan, about 500,000 buildings are constructed every year, and among which 400,000 are detached houses. So the building which require structural calculation is 15,000. Okay? So among 50,000, isolated building is only 150 every year in average. So it means 1% of the building is isolated. So 1% is not a big number. So our JCSI would like to increase this percentage. I hope 50%. It's my dream. So why seismically isolated building is not widespread even in Japan? The first reason is, of course, cost. Cost is expensive. However, in high seismicity area, design earthquake is very, very large. But if you adapt isolation technique, inertia force will be reduced. It means the seismic force is reduced. You can design the structure adapting slender member. Okay? So construction cost might be cheaper than conventional building. I'm talking about high seismicity area. Also, if you think about the future damage cost by future earthquake, so life cycle cost probably much cheaper than conventional building. So we must explain this effectiveness to the owner of the building. So second reason is design and technology is very, very complex. So seismically isolated structures require intricate design and construction technologies demanding specialized knowledge and expertise. That's why JSSI is working very hard to educate engineers Reason 3, regulations and standards. Yes, even some country doesn't have design code of seismically isolated building. Okay? And this is also another reason JCSI would like to introduce how to design isolated buildings outside Japan. Okay, now I would like to talk about seismic isolation interface. What is seismic isolation interface? So this is a building, and under the building, there is a isolation devices. So isolation interface is this blue area. Okay? So building is moving during earthquake. So there is a gap between ground and building. So people may drop and may be injured. So we need an expansion joint for the people not to drop under the isolation pit. Okay? Usually we put the gap between building and ground around 50 or 60 centimeter. There is two types of expansion joint. One is expansion joint without step. Okay? So when building is coming close to the ground, so this expansion joint lift up, and when building is receding far from the ground, this gap expansion joint still, not to drop under. So there must be some overlap. Another technique is isolation expansion joint with step. It's much easier. There is a inclined step between building and ground and overlapping. So if building is moving left and right, what to say, no need to worry people go under because there is a expansion joint. Yeah. But there must be some slope between ground and building. Under raining, people may slip at this slope. So recently, people prefer the above expansion joint without step. I will show you the picture. This is a typical expansion joint without step. You don't know where is the expansion because there is no step. Another example. So building is front side and the opposite side is the ground with a slope. So there is a connection, there is an expansion joint. I will show how it moves. Okay. So during earthquake, this expansion joint will move. So this expansion joint is regarded as non-structure, and the structural engineer don't care how to the quality of this expansion joint. However, when earthquake happens, even medium earthquake, this expansion joint is a place we observe damage. Building is okay, but many damage happen in expansion joint, around expansion joint. This is a photo in Japan. So even in Japan, we have a problem of expansion joint. And engineers say, oh no, it's minor damage. Building is okay, right? However, the owner get angry. No, it's not acceptable. It costs money to fix it. Other conventional building, almost no damage. Why isolated building have damage by medium earthquake? So I would like to insist structural engineer should pay more attention to expansion joint. Yeah? Because this damage to expansion joint can occur even in small or medium earthquakes and expensive to repair. So this is a serious problem for the widespread use of seismically isolated structures because it gives a bad impression. that seismically isolated buildings perform less well than conventional normal building in small or medium earthquakes. So in Japan, people, how to say, misunderstand seismically isolated buildings. So to avoid this problem, JSSI published guidelines for seismic isolation expansion joints. Sorry, it's in Japanese right now, but in the future, I hope JSSI will translate into English. So in this guideline, we categorize expansion joint in 3 classes. Class A, this is a very high quality expansion joint. It must be functional under moderate earthquake, also functional under large earthquake, and the performance must be tested by using shaking table. And this kind of high quality expansion should be adapted with heavy pedestrian traffic area, like entrance of the building. But other area, maybe rank B is okay. So it is an expansion joint functional under moderate earthquake, but it can accept the damage under certain damage under large earthquake. Or under the performance should be checked by shaking table or static test. Yeah. Also, the area which have almost small pedestrian traffic, you can adapt to rank C. So you can accept the limited damage to under moderate earthquake and large earthquake. Yeah. So this is a level A, class A expansion joint. You must to check the performance by shaking table. Okay. When I visited Turkey this year, last year, they did this kind of test on the site by human force, not the shaking table. But they make some pick up some sample of expansion joint, and they are doing moving test on the site of the construction. So it's a good practice. I was very impressed. Okay, another topic is design of non-structural component and equipment in isolation interface. So inside the isolation interface, there is a electric wiring or a flexible pipe joint, or there is a space under elevator not to hit against the foundation. So those pipes and wiring must be flexible to accommodate movement of isolation building. Yesterday, we visited the isolation building in Jakarta, and we go enter this isolation interface. We observed a small problem. Some pipe may hit in case of earthquake. So I recommend to check carefully again the building, because the building is very important building. So to avoid problem, well, for example, piping damage may cause problem of infrastructure of the building. So I recommend to check carefully. So to avoid this kind of damage, JSSI also published facility standard of seismically isolated buildings. And this is another practice in Japan. It is a governmental notice issued in 2000. So it is a regulation, mandatory. Every isolated building must put this kind of sign in front of the building. Okay? It says, warning, building moves during earthquakes. Okay? So please do not leave object in the range of motion. And you use caution during earthquake not to be struck or crushed by the building. So this kind of notice must be signage must be put close to the entrance of the building so that the people who use this building, oh, this is isolated building. Okay. Okay, next topic, I would like to talk about seismically isolated high-rise buildings. There is no height limitation in Japan. So performance must be checked by dynamic analysis using computer. But high-rise building, this is the number of high-rise building adapting seismically isolated technique. First of all, what is a high-rise building? In Japan, the building height is more than 60 meters. We categorize high-rise building. Okay? And the number is increasing after Kobe earthquake. Condominium is number 1, and the office is second. Okay. But you must be careful when you adopt isolation technique for high-rise building. Number 1, high-rise building is very heavy, so you need a big size of bearing. Number 2, when earthquake happens, building move horizontally and there will be big overturning moment at the bottom. So tensile force may occur to rubber bearing. Rubber bearing might be damaged by this tensile force. And high-rise building, we call natural period. It's a shaking period is already very long. So when you put isolation devices, you must design to achieve much longer isolation period. Sometimes 6 seconds or 8 seconds. And the last thing you must consider is wind force, because wind force is getting larger along the height. Okay. So to solve this problem, this is a typical device adapted for high-rise building. It is cross-linear bearing. There is a rail and a block connected and moving smoothly. So in case of tension, this block can, resist against tension. So it can achieve long isolation period. Also, it will resist against tensile force. It's a very huge device. It is adapted for high-rise building. Yeah. Also, to resist against wind, sometimes we use shear pin. So this is a pin connecting building and ground. When wind comes, this shear pin stops movement of the building. But when earthquake happens, because earthquake is stronger, this shear pin is designed to be broken by earthquake. Then building can move smoothly. Okay? This shear pin is also very, very popular for high-rise building. This is example adapting cross-linear bearing. The height is 130 meters. And another example, this is a condominium. And this is an isolation layer. You can see in the middle, orange one is, I'm sorry. Okay. One moment, I would like to disappoint. Okay. So this middle part is a lock pin. So this is a shear pin against wind load. Okay. Another example, also in the plan, you can see shear pin in the middle. and the rubber bearing outside, and the sliding bearing in the middle part. So in Japan, it is very common to use multiple different devices for the building to find out the best combination. Another example, okay? Also you can see sharpening in the middle and rubber bearing outside and the viscous damper also. Yeah. Okay. Now I would like to talk about the wind force. When you adapt metallic damper, like a red rubber bearing or a steel damper, you must worry about creep and fatigue, okay? And the wind force. There is a guideline for the wind-resistant design of seismically based isolated buildings. So what we worry about is, wind consists of average wind and fluctuation wind. So if building is moving elastically, we call rank A, no problem, no worry about creep or fatigue. But when fluctuation, rank B, this is a building or isolation red rubber bearing may go enter nonlinear range and the fluctuation is elastic. Maybe you worry a little bit about fatigue effect. And the rank C, this is most severe case. So red rubber bearing may go enter nonlinear range and the fluctuation wind also dissipate energy. So plastic deformation is accumulating by cyclically. So you must worry about fatigue problem. Okay. So this yesterday we visited. We visit factory which produce red rubber bearing. So in the future, I believe this consideration is necessary in Indonesia also. Okay. Okay. I still have time. Okay. I would like to talk about next subject, long period ground motion. Usually, this is a graph against the period and the building acceleration. Ordinary earthquake, no, not ordinary. For example, Kobe earthquake, epicenter earthquake, or Taft earthquake, many earthquake has dominant period is less than 1 second. Okay, so building maybe less than 10 story, may be affected, but the building, high-rise building or isolated building move very slowly. So period is more than 2 seconds. So acceleration is very small. So this is the advantage of isolated building. Yeah? For example, Kobe earthquake peak is 0.2 seconds. So short story building collapsed. But in Kobe, there was a high-rise building, almost no damage because acceleration is very small. That's why we recommend isolation technique to extend natural period, yeah, so that the building moves slowly. However, so this is ordinary earthquake. Recently, we worry about long period ground motion. So this is the earthquake, which this is Tokyo area. Tokyo area has a deep sedimental soil, soft soil. And when earthquake happens, it traveled through the rock and coming to this sedimental soil. Then surface wave is generated from the edge of this basin and coming back, traveling on the surface. This surface earthquake has a long period component. That's why we call long period ground motion. So it will affect high-rise building or long span bridge or oil storage tank. Actually, we had a damage of oil storage tank at the 2003 of Tokachi earthquake. You can see the fire happen because of long period ground motion. So if this similar earthquake happen in Tokyo area, Osaka area, probably we will have problem. Okay. And this long period ground motion occur the place which has very deep sedimentary soil. So we already know. This is a map of Japan. You can see red color. This is, for example, Hokkaido, Sapporo. There is a Ishikari plain, which may produce long period ground motion. Tokyo, there is a Kanto plain, biggest plain in Japan, which may produce long period. Nagoya, Osaka. Yeah? So such place, actually high-rise building may be affected, but it's too late. There are so many high-rise buildings already constructed in Japan. This is a movement of Tokyo high-rise building during 2011 Great East Japan earthquake or Tohoku earthquake. You can see the building is moving. At that moment, the building movement is around 1 meter at the top. But we surprised the building in Osaka, 700 kilometers far from epicenter, moving 3 meters at the top, left and right. Can you imagine 3 meter movement? This is a 3 meter movement. I designed this shaking table long time ago because Osaka area, I mean, the building is constructed, has a dominant period is 6 seconds. And the building natural period is also 6 seconds. So it match each other and the resonance happens. That's why high-rise building moved very largely. Same thing may happen to isolated building. Yeah, I will skip this one. So we tested isolated building on, oh, sorry. 아, 동일했다. I want. Okay. Okay. So this is isolated building under long period ground motion. Okay. And resonance happens at the moving largely. Finally, it will hit against ground. Down. So long period ground motion is very critical for isolated building. And also many cycles. I mean, it continues long time. So during a cycle, the stiffness and damping is getting degrading, reducing. So this is a hysteresis of high damping rubber bearing. And also this is a hysteresis and the situation of red damper. After 30 cycles, the damper deformed much. Okay? This is a sliding bearing. After repetition, many cycles, friction force is degrading. Also, you can observe scratch on the sliding surface. Okay? So recently, when you make a design isolated building, we request please consider long period ground motion and also increasing this deterioration effect in the design. Okay, my final part is about international standard. This isolated building, I mean, technique have been constructed widely around the world. But there are many design code, Euro code, American ASC, Chinese code, Japanese code. So the philosophy is not consistent. So we would like to promote good quality isolated structure around the world. So we believe we need some common international standard. This is activity to develop ISO standard, International Standard Organization, ISO. Already ISO 22762, it was published in 2005. This is the ISO standard for elastomeric seismic protection isolator. It is about rubber bearing and describing how to test rubber bearing and what is the criteria. Yeah. Also, there is a standard ISO 3010. This is a general design philosophy of seismic action on structures. And recently, we published ISO 2361618. This is general principles on seismically isolated structures. I was a convener of this working group. This is the content of this ISO standard. It describes basic philosophy only. Yeah? So you can see chapter 5 is basic principles. Chapter 6, target performance. Chapter 7, design seismic force. Chapter 8, seismic analysis. 9, 10, 11, this red part is very, very, how to say, special in this guideline standard, because chapter 9 describes construction management. Chapter 10, maintenance, and chapter 11 is performance requirement of isolation devices. Usually, structural engineers don't care about management or maintenance, right? Or isolation devices. But performance of isolated building largely depend on the performance of isolation layer and device. So we intentionally put this chapter so that the structural engineer should pay attention to this issue. This is annex. I will skip this one. So now we are making ISO TR21259. It is seismic design examples based on ISO 23618. It will be published next year. So you can find many design examples in this guideline. Okay? And another thing to disseminate isolation technique is, I already mentioned, JSSI conducted workshop 10 years, and we did workshop in Indonesia 2017. So we'd like to continue this one. And this is the International Association, Anti-Seismic System International Society. Right now, Dr. Ian Aiken is the president. I'm left bottom, I'm a board member. So every 2 years, we organize world conference. Yeah? And at the end of my presentation, I would like to introduce my computer software. It is free download. You can show how isolated building will work. I got the education award by this software. So left one is a conventional building. So you may have damage to superstructure, yellow part, but the isolated building, it will move on the ground, no damage to superstructure. So the owner will understand, oh, isolated building is quite good. So please use my software. It's good for a student or engineer to learn about seismically isolated building. Thank you very much. That's all my presentation.
Thank you very much, Vice President. That is very insightful presentation. So today we have a participant, not only on site but also online. So I will I will open Q&A session. First, for the participant in on site right now, is there any question? Feel free to raise hand if you want to ask question to Saito Sensei. Okay, maybe, oh yeah, okay, please, sir. Please mention your name first and your institution.
Okay, thank you. My name is Aris from ITB. You mentioned before about the shear pin on the isolation system, yeah? You mentioned that the shear pin will withstand during the wind, but after a quake, maybe isn't like that. So
Yes.
so so if earthquake happens, so we should change the pin later after the earthquake. So it is difficult to change those pin because it already attached to the building under the column, for example. Okay, thank you.
Maybe I will ask engineer to answer this question. I'm working for university. Maybe engineer knows the answer well.
I'm obviously I don't have an experience of this type of shear pin, but I imagine after earthquake you can bring a jack, but it's also huge jack into the isolation layer and push it back to the original portion. So probably easily smooth to the original pin, blocked pin, and replace it later, maybe. Do you think about that?
I think so. I'm also structural engineer in Japan, and I have experience trying to install this kind of pin to the project. And at this moment, the strong wind is induced by the typhoon. So typhoon can be predictable. So when the typhoon is coming, the actual usage of this pin is when the typhoon is reported to come, building manager is to drop the pin, and after typhoon going over, building manager again pick up the pin. So typically, it's avoidable to damage during the earthquake. But even though the pin is damaged during the earthquake, the pin itself weight is around 10 kilogram or 20 kilogram, so easy to pick up by hand. So I suppose even if the pin is damaged, and it is easy to replace.
Okay, thank you.
Okay, thank you very much.
Okay. Thank you. Next question. Is there any question from the participant in on-site? Oh yeah.
Yeah, thank you for the presentation. My name is Erwin from. Test. We saw the video that the structure may, because the displacement is very large, so it may bump to the nearby structures. In some cases, I saw that usually they install dampers, maybe to limit the displacement of the best isolator. Is it common practice in Japan to combine best isolation and dampers? That'd be the first question. And if it is a common practice, then I think that if the damper is too stiff, maybe the isolator cannot work efficiently. But if it is too soft, maybe then we cannot control the displacement. Do you have any comment on that, Professor Saito?
Okay, thank you for your question. The first question, usually engineer design to have enough gap. So under design earthquake, well, we have a level 1 earthquake, medium, and level 2 earthquake, large earthquake. We design isolation building not to hit against the retained wall. Yep. So for example, 60 centimeter probably enough to avoid hitting. But I'm talking about unexpected huge earthquake in the future. So earthquake may be more than design earthquake, stronger. So in such a case, this kind of hitting, pounding may happen. So if the building owner worry about such extraordinary case, we recommend to adopt a special device. Maybe engineer Muramatsu-san knows about this issue because he actually designed such isolated building. Maybe he.
I will explain later in my presentation. Okay.
Yeah. So yes, there are many techniques. Yeah, and each company developed different ideas, and it's very hot topic right now in Japan. Yeah. And the next question is if the building is soft building, you are talking about
The dampers.
dampers.
If they use dampers, like a viscous dampers, to limit the isolator movement, something like that. Is it common?
You are talking damper in isolation layer interface. Yes, it's very common. It's very common. And yes, you should watch about the presentation of Mr. Muramatsu. He will introduce special damper which change damping force depending on displacement. So if displacement is very excessive, increasing damping force. So such how to say, yeah, you need a special oil damper. He will explain later. Yeah.
Okay, it's very interesting. And Mr. Erwin, you will find more information after the next session. Thank you very much. Is there any question from the on-site? If not, I will move to the online participant. Hello, everyone in online. Is there any of you want to ask something to the speaker right now? If you want to ask, you can ask directly. If not, I will go to on-site first. There's one person who already tried to give some question. Please, Mr.
Yeah, thank you. My name is Nathan. I have one question. How is the effectiveness of the damper, the isolator to reduce the vertical earthquake? Thank you.
Effective against what?
How is the effectiveness of the rubber bearing isolator to reduce vertical earthquake, not horizontal one? Thank you.
It is very good question. Well, usually we don't worry very much about the vertical ground motion because the building is constructed supporting its own weight from the beginning. So it's strong against the vertical force. And isolation, yeah, sometimes if you adapt isolation technique, vertical motion even amplify. You can reduce horizontal acceleration, but the vertical acceleration might be amplified by rubber. So But actually, it doesn't contribute to the damage of the building. But there is a special building which contain very expensive equipment and want to reduce vertical motion. There are three-dimensional isolation device already developed. But as far as I know, it's very expensive and adapted only 1 or 2 buildings in Japan. Yeah.
Okay, Pak Nathan.
Yeah, okay. Thank you. Because I saw there is one paper that will be presented about large span structures. So maybe because the vertical earthquake will be dominant for the large span structure. Yeah. Thank you.
Thank you very much, Mr. Nathan. So in the online, we have 2 questions on the chat room. Please, Mr. Faldi, can you show us the question? Okay. There is a question from Mr. Faiz Sultan. My name is Faiz, an alumnus from IISEE for the 2022 until 2023 program. During my study at IISEE, I conducted research on base isolation systems, and you were one of the examiner at my final presentation. I would be very grateful if I may kindly ask you several technical questions related to base isolation for seismic retrofit. First, if a base isolation system is used as a retrofit method for an existing building, reinforced concrete, is the superstructure above the isolator still required to satisfy a certain level of ductility corresponding to an ordinary moment resisting frame, an intermediate moment resisting frame, or special moment resisting frame? Maybe one by one. First question, probably you can respond first, Saito Sensei, and then we can continue to the second one.
How to answer? Well, if you retrofit existing building, if the building is designed by, how to say, it is, なんて答え? Usually we keep the same structure, not to retrofit superstructure, because after you adapt isolation technique, seismic force is reduced. So even building will be much safer than before. So usually not necessary for retrofitting superstructure, except superstructure is very old or not satisfying current design standard. Maybe you may need some limited retrofitting, but usually no need to touch superstructure. Yeah.
I see. Okay. We move to the second question. Can an existing ordinary moment resisting frame be directly retrofit with base isolation system without adding additional strengthening element? Or is it still necessary to upgrade the ductility of the structural component? For example, to be equivalent to IMF or SMF?
Well, if you install isolation, well, the base isolation, you must excavate ground, make a new foundation under the isolation device. Also, isolation device must be put on a very strong beam, right? So you may necessary to retrofit the foundation of the structure, existing structure. Yeah, so it may cost a lot of money. So that's why retrofitting example is limited even in Japan. Yeah.
I see. Thank you very much, Saito Sensei. So let's go to the next question. Is there any question again? Besides Faiz Sultan. Second question from Mr. Simpson, Merah Putih Prekes, that is the company. The question is there any difference in design calculation of bearing pad for building structure constructed using conventional method compared to precast system? Okay. Is there any difference in design calculation?
Bearing part means isolation bearing.
Yeah, probably. Or Mr. Simpson, are you still online? You can ask directly. Okay, I think it's base isolation. Base isolation for precast structure for building.
Well, actually, isolated building, I mean, how to say, if you adopt isolation technique, superstructural design is very flexible, much flexible than conventional building. So, of course, precast system or a conventional method, everything, and not everything, but there are many flexibility in the design. Even irregular building, if after adapting isolation device properly, you can reduce eccentricity. So I think isolation technique will widen the freedom of design.
Yes, of course. Thank you, Saito Sensei. Since Mr. Simpson,
Thank you, sir.
listen.
Yes. So
Yeah.
there's no problem, yeah, if we use the precast system and the conventional system. There's no something different for the design calculation.
Mr. Simpson, can you repeat one more time, but slowly, please, and bit louder?
I mean that there's no specific design calculation for the bearing pad if we use the precast system, not the conventional method.
Well, it depends on how to design the building, but usually first we assume superstructure is rigid and the building will move like a one mass system and design isolation layer only. So superstructure, we don't worry so much about the detail because the superstructure will move like a rigid body during earthquake. So this is a most simple design procedure.
Okay, Mr. Simpson, probably if you want to ask more, you can ask outside of from this event, probably. Okay. Is it okay,
Okay,
Mr.
thank you
Simpson?
very much.
Yeah,
It's
thank you
okay,
very
but,
much, Mr. Simpson. Yes.
In our Indonesia, yeah, we have calculation because we used to be with sistem rangka pemikul momen khusus. Maybe the Indonesian is that. I don't know for the English, yeah.
Okay, Mr. Simpson, thank you for the comment. Can we go to the next question? Is there any question again in the chat room? Mr. Paldi and Mr. Faisal? Oh, we have another, but do we have time? Maybe this is the last question, probably. Mr. Haryo Widiandoko from PT Waskita Karya. The question is, earlier it was explained that wind force does not affect the damper, but a strong shear force can damage it. Has there ever been a case where the damper damaged, and how can it be maintained or repaired? How much would it cost? Thank you. So, Saito Sensei, how about this one? Is similar with Mr. Erwin question, I think.
Well, after large earthquake, we have a Japanese scale from 1 to 7. So if the earthquake is more than level 5, engineer must visit isolated building to check the status of isolation device and damper. So if something wrong happens, we replace the damper or isolator. So this kind of maintenance criteria, procedure, we have, yeah.
Okay. So
about the cost, I don't know.
Yeah. That will depend to the what's that, the consultant and the local price probably. Okay. Do we have another question from the chat room? No. Okay. What? This one again? Okay, this is last one. So many questions. From Mr. Gambiro Suprapto, API3I. Question, the principle of base isolation is to lengthen the natural period of a structure, thereby reducing the building acceleration and ultimately decreasing the seismic forces. This approach is advantageous for low-rise buildings. Meanwhile, the reduction in acceleration is not significant for high-rise buildings. So, what are the benefits of using base isolation for high-rise buildings, Sensei?
Good question. Good question. Yeah. So when you adapt the isolation technique for high-rise building, you extend much longer. So anyway, if the owner requests higher performance for high-rise building, yeah, base isolation is also one option. Yes, if you success to extend longer period, natural period. Yeah.
Okay. The second question is, which type of moment resisting frame is used for designing a building with base isolation? That is
Well, superstructure, it's better to be rigid. So we recommend to make a rigid, frame with maybe shear wall. If building has a shear wall, it's much better to adapt the isolation.
Okay.
Yeah.
Okay, thank you very much, Sensei. So our time is limited actually, and we still have two more speakers. So I think I will cut all the chat right now, but probably if you still have time, Saito Sensei, you can answer the question through the chat room if you have time.
Okay.
Yeah.
Oh, yeah.
Okay, we still have another speaker. Thank you very much, Saito Sensei. The second speaker is Mr. Akitsugu Muramatsu. So Muramatsu-san is Chief Manager Design Department. Oh, this is incredible. Nuclear Facilities Division of Taisei Corporation. He obtained his Master of Engineering from Kyoto University, Japan. And he will share knowledge about practical cases of seismic retrofit and seismically isolated building with advanced damping systems. So, Muramatsu-san, the stage is yours.
Thank you for Chairman. This is my presentation title, Practical Cases of Seismically Isolated Building and Seismic Retrofit with Advanced Damping Systems. My name is Akitsugu Muramatsu from Taisei Corporation. So I'm a structural engineer and from Taisei Corporation, which is a construction company in Japan. But in Japan, some construction company has R&D division and design division. I'm from design division engineer. So I started my career as a structural engineer since 2000. Sorry. So these are my today's topics. The first one is introduction, and the second one is some features of seismically isolated building in Japan. So in my presentation, the word of SI means seismic isolation. Then I'd like to introduce two practical cases, and I'd like to introduce an important topics, quality control, and etc. in the last section. So the first topic is introduction. This is a background of my presentation. So past earthquakes revealed the gaps between the performance defined as the minimum requirement by law and the performance potentially expected by society. So this table shows the minimum requirement performance and the expected performance according to each earthquake level. So there are gaps between two sets of performance. So usually expected performance is higher than minimum requirement. So for example, Japanese code does not define the performance of this level beyond design basis level. So however, I think that society expects us to design buildings with enhanced performance against beyond design basis event. So we structural engineers are expected to meet not only the minimum requirement, but also the society's potential expectations. So what can structural engineers do to implement the expected performance? Of course, within the limitation in project budget. So in the right column, some examples to achieve the expected performance are listed. For example, to provide redundancy with buildings is one of solutions against beyond design basis event. So from these points of view, I'd like to introduce an advanced structure with SI system and a seismic retrofit with special oil dampers. So, and the second topic is some features of seismically isolated building in Japan. So probably you saw the similar figure in the previous presentation in Professor Taigi Saito. So this figure shows the number of construction of SI buildings in Japan. The vertical axis shows the number of SI buildings. The horizontal axis shows years. So until 1995, the number of SI buildings was not so many. In 1995, a large earthquake occurred, Kobe earthquake. After that, many people found that performance of SI buildings to protect lives and properties was impressive. Then the number of SI buildings rapidly increased after the earthquake. So although there are a few sharp increases right after major earthquakes, the average number of construction of SI buildings were about 200 in last 2 decades. And as of 2024, the total number is over 5,600. This is excluded detached house. And I'd like to show some features of SI buildings design in Japan. However, Japanese seismic design codes are unique to Japan. And I think Indonesian seismic codes are similar to the United States design code. So I will introduce some points of Japanese code while comparing them to the US seismic design standard, ASC7, which is widely used around the world. So as for design procedure, 2 procedures are allowed to design SI buildings in Japan, static procedures and dynamic procedures. So Japanese static procedure, equivalent linear method, it's similar to the US static procedure, equivalent lateral load procedure. As for dynamic procedure, nonlinear time history is allowed in the seismic design code. And static procedure is simple and very useful, but there are several restrictions on application of static procedure. So nonlinear time history analysis is widely used for design of many SI buildings in Japan. And this is a comparison of return periods of earthquakes for design. Two levels of earthquakes are defined in Japanese seismic design codes. But from the practical viewpoint, all structural members and isolation systems are designed using 500 years earthquakes. On the other hand, all structural members and isolation systems were designed using about 2,500 years earthquakes in ASC 7-22. This may require a bigger displacement capacity than one required in our Japanese seismic codes. And as for typical type of SI system usually consists of isolators and dampers, and there are various kind of devices which we can choose, such as rubber bearing, sliding bearing. As for dampers, oil dampers, steel dampers, and lead dampers, and so on. And adequate devices should be selected to mitigate seismic response efficiently according to each building's type, use, and the required performance. This slide shows some common types of SI systems. So blue boxes indicate isolators, red boxes indicate dampers, and orange boxes indicate bearings which have both functions of isolators and dampers. Type number 1, 2, 3, and 4 have been popular systems in Japan, and type number 5, friction pendulum system, are getting popular in these days. On the other hand, type number 3, 4, and 5 are popular system in the United States and around the world, I think. And type number 2, the combination of natural rubber bearing and flat sliding bearing is our company's original system. We call it hybrid TAS system. A good point of this hybrid TAS system is to easily achieve a longer natural period of SI buildings in comparison with other systems. So, okay. Oh, sorry. So this video shows a dynamic test of natural rubber bearing and sliding bearing. So isolators can smoothly deform in horizontal directions and can support vertical loads under large horizontal deformation. This video shows the dynamic behavior of the hybrid TAS system during an earthquake. So left side is SI structure and right one is non-SI structure. So these are isolators, natural rubber bearing. You can see the big difference between two buildings' behavior. And the good performance of the hybrid TAS system has been proved by past large earthquakes. These photos were taken in two hospital buildings, which were next to each other. So left one is inside of a non-isolated building, and right one is inside of an isolated building. So you can see the big difference between two photos. So if you were a doctor, how would you work under the left photo's condition? So the isolated building kept operational right after the earthquake. Keeping operational right after earthquake is one of great benefits of SI structures. And the next topic is a practical case of SI building. So first one is a short stroke SI system with passive switching oil damper. And this is a background why we have developed this short stroke SI system. So after several major earthquakes in Japan, demands for SI systems are continuously growing, as I mentioned in the figure in the previous slide. And even for buildings in relatively small sites, often located in densely urban area, so SI systems are highly required to protect property. To protect property and operational function, and to achieve companies' business continuity plans, or BCP. To implement SI systems in small sites, response displacement of isolation layer due to major earthquake needs to be mitigated for keeping building area as large as possible. As for conventional SI buildings, design clearance between building and moat wall is usually 60 centimeter or so. So in relatively small site, if we wanted to keep same clearance of 60 centimeter, the possible building area were reduced. So by mitigating the response displacement of isolation layer, so we can keep building area as large as possible. That's why large damping is necessary to mitigate the response displacement. As for building response due to major earthquakes, if we install large damping into the isolation layer, we can prevent collision. But as for frequent minor or moderate earthquake, so large damping will result in large response acceleration. So this may be not good isolation performance. So normal damping may be good to mitigate response acceleration due to minor or moderate earthquake. So normal damping is preferable to large damping for minor or moderate earthquake. However, large damping is necessary to prevent collision during major earthquake. So this is the issue to be solved in this project. So in the case that the site is not so spacious, to mitigate response displacement during major earthquake by large damping is necessary. But to reduce response acceleration during moderate earthquake is also required, and this is a contradiction, a kind of contradiction. So we employed a viscous damper whose properties can be changed. Variable damping means lower damping coefficient for moderate earthquake and higher damping coefficient for major earthquake. So we developed a passive switching oil damper. This is a kind of variable viscous damper. And the passive switching oil damper has a special characterized damping coefficient, which is switched from low damping to high damping after exceeding designated displacement. To acquire the special character, some parts for detection of displacement shown in red are added to a conventional oil damper. This figure shows damping properties of passive switching oil damper, and vertical axis shows a damping force, and the horizontal axis shows velocity. And this damper has two modes. Blue one is a lower damping mode, which is assigned to initial condition. And red one is a higher damping mode. The damping coefficient is switched from the lower one to the higher one after exceeding a designated displacement. So in this project, we set 10 centimeter as the designated displacement. This passive switching oil damper has high reliability. The damping coefficient is mechanically switched from lower to higher without electrical power. So this leads to high reliability and easy maintenance. And the shut-off valve keeps closed once switched So after earthquakes, the initial load damping mode is recovered by using a manually operated lever. And this is a summary of merits of passive switching oil damper. So low damping coefficient results in full demonstration of isolation performance during moderate earthquake, and the high damping coefficient results in mitigation of response displacement during major earthquake, including beyond design basis event. So safety is ensured during major earthquake without compromising the sense of security during moderate one. And we applied this system to a few buildings. I'd like to introduce one example, which is called ZEB demonstration building. This is a SI building with a passive switching oil damper, which has been constructed in our technology center. This slide shows the structural systems. This is a 3-story building. Isolation layer is here, base isolation. And the lateral force resisting system of superstructure is moment resisting concrete frame with a concrete shear wall, and very slender column with high strength concrete of 300 megapascal is just gravity element. This slide shows a structure plan in first floor. So despite uneven distribution of lateral stiffness due to the slender columns located in one side, a torsional behavior is significantly mitigated by adapting the SI system and arranging the lateral force resisting system in the channel shape. And this photo shows the entrance hall, which can get open by adapting the slender columns. This slide shows a plan of isolation layer. The isolation system composed of natural rubber bearing and flat sliding bearing and passive switching oil damper. The design clearance between the building and the moat wall is 300 millimeter, which is almost half of the typical clearance of conventional SI structures. This is a parametric study with single degree of freedom system, so SDOF system, to evaluate appropriate damping coefficient for moderate earthquake. In this study, 2 parameters are employed. One is earthquake level, another one is damping coefficient, and vertical axis shows the response acceleration, and horizontal axis shows the response displacement. This line shows the response with half of major earthquake. So, I mean, I think this is a kind of a moderate earthquake. So if more damping is added, the response acceleration becomes larger. And if damping is reduced, the response displacement becomes larger. So in this project, the lower damping mode is better to acquire a smaller response acceleration for moderate earthquakes. And this is a comparison between passive switching oil damper and conventional oil damper. So right figure shows the damping properties of oil dampers. Black line shows the property of conventional damper. Red line shows the property of the higher mode of passive switching oil damper. And the left figure shows the result of nonlinear time history analysis with stick model and major earthquakes. The horizontal axis is maximum response displacement. As for the response with major earthquakes, the maximum displacement almost same and enough smaller than the design clearance of 30 centimeter. And this is also another comparison. The right figure shows the damping properties of oil dampers, and black line shows the property of conventional damper, and blue line shows the property of the lower damping mode of passive switching oil damper. And the left figure shows the result of nonlinear time history analysis with stick model and moderate earthquake. The horizontal axis is maximum response acceleration. As for the response with moderate earthquakes, the maximum acceleration with passive switching oil damper is decreased significantly by 30 to 40% in comparison with the result of the conventional oil damper. This building also employs a seismic observation system. Accelerometers and displacement sensors have been installed in the building. And after earthquakes, recorded data are automatically analyzed and the results are automatically reported by email right after earthquakes. So owners and engineers can get useful information about whether it is necessary to investigate the building more closely. And this slide shows an example of the automatic report. The red line shows the recorded acceleration in the main building, which is not a SI structure. A blue line shows the records in ZEB, which is next to the main building. So you can see the effect of seismic isolation is fully demonstrated in moderate earthquake. And a scratch plate is also installed in the isolation layer. The scratch plate is a marking type displacement recorder. So this system does not require a power supply. In addition, installation and maintenance costs can be kept very low. And this system, the short stroke SI system with passive switching oil damper, has been applied to some buildings in Tokyo. The center one is an application to a high-rise building. The right one is an application to an existing building of a local government. So this is a summary of this system. So safety is ensured during major earthquakes without compromising the sense of security during moderate earthquake. And the system allows owners to adapt the SI system in small sites while keeping the building area as large as possible. And the next topic is a practical case of a seismic retrofit for tall building with deformation-dependent oil damper. So this building is 260 meters with a fundamental period is of 6.5 seconds in transverse direction and 5.4 seconds in the longitudinal direction. It is a building with a very long fundamental period. And this building was constructed in 1979. So it makes this building a relatively old high-rise building. So we implemented response control retrofitting using special oil dampers as countermeasures against long period ground motion for this building. So this slide shows an example of seismic motion used in the design of tall buildings in Japan. This graph shows the velocity response spectrum for design seismic motion. The horizontal axis represent period, and the vertical axis represent response velocity. And before 2000, Japanese high-rise buildings were often designed using 3 standard recorded waves, El Centro, Taft, and Hachinohe. And in 2000, building standard law was revised. The velocity response spectrum with longer period components came into force. This black dashed line. So therefore, buildings constructed before 2000 and designed using the only 3 standard recorded waves may have been designed with a smaller input seismic motion in the long period range compared to current high-rise building. So deal with the long period ground motion containing plenty long period components. We developed a seismic retrofit for existing high-rise buildings with a damping system. So to mitigate seismic response of existing high-rise buildings, the most effective and realistic countermeasure is to increase damping by adding energy dissipation devices. So to incorporate more damping, let's consider installing viscous damping devices. The left figure shows a typical viscous damper. The upper graph illustrates the relationship between velocity and damping force. The lower graph shows the relationship between displacement and damping force. And the right figure shows a common oil damper frequently used in Japan. It has a bilinear characteristics. As shown in the upper figure, once a certain velocity is reached, the increase of damping force is limited by employing bilinear characteristics. So the minimum damping force can be restricted to a certain level. So this type of oil damper have high damping performance. However, it also has a kind of disadvantages when used for retrofitting existing buildings. As shown in this figure, after the installation of the ordinary oil dampers like this, the axial force imposed on the lower columns tend to be so large. So reinforcement of these columns or foundation may be necessary. This may become a downside of this type of retrofit. To avoid the downside introduced in the previous slide, the deformation-dependent oil damper has been developed. So this new damper has a unique hysteresis loop shown in red. When the deformation reaches the designated value, the damping force decreases as deformation increases. So by utilizing these special features, energy absorption capacity can be kept at the almost same level as ordinary oil damper, and the downside can be addressed. This slide shows the mechanism of deformation dependent oil damper. The left figure shows the oil flow under normal conditions. And as shown in the right figure, when displacement exceeds a designated value, another valve opens, allowing oil to flow into the gap and reducing damping force. And as a result, damping force decreases as displacement increases, and the additional load on surrounding columns from oil dampers are also decreased. So as an additional axial force can be reduced. So therefore, reinforcement of the existing frame can be cannot be necessary. Therefore, no reinforcement of the existing frame is necessary. And displacement dependent oil dampers were installed on floors from 15th to 39th of this high-rise building. This is a typical floors plan. The core composed of elevator shafts or stairs, etc., is located on the center of this building. And these areas are offices. And perimeter columns span is 3 meters, and the longest span is 15.4 meters. So deformation-dependent oil dampers are installed in perimeter areas in this red mark. And based on the dynamic analysis, those dampers were installed to these floors where the story drift angles are relatively large. And design target of the seismic retrofit were listed in this slide. So according to BCP, the objective is to sustain the building function even after large earthquake. So we settled the maximum story drift angle within 1/100. So no reinforcement of the existing frame to avoid obstructing continuous use of the office during seismic retrofit. As a result of the seismic retrofit, it has been confirmed that the maximum response story drift angle satisfies the target of 1/100, even against the maximum considered long period ground motion. This figure shows the maximum response displacement on the horizontal axis and the story height on the vertical axis. And these two square symbols represent observed records during the Tohoku earthquake in 2011. And red line indicates the simulation results after seismic retrofit. And the simulation generally reproduces the observed record. On the other hand, green line indicates simulation result without seismic retrofit. And the video shows the simulation result. Red represents the building with the seismic retrofit. And the green one is the result of simulation without seismic retrofit. And this demonstrates that the seismic retrofit with deformation depending on dampers effectively reduces the response displacement. And the actual number is, so this seismic retrofit can reduce the response displacement by 20% in comparison with without seismic retrofit. And this is a summary. We have developed a deformation depending oil damper to reinforce existing high-rise building against long period ground motion. And this deformation dependent oil damper reduces the damping force at the moment when the frame deformation comes close to its maximum value. Allowing this feature, reinforcement of columns, girders, and foundations are no longer required. And we applied this damper to an existing old high-rise building at Tokyo. The seismic response was observed in the Tohoku earthquake in 2011. And it is clarified that the damping ratio was higher and the maximum displacement lower by 20% as compared to the building without dampers. And this is my last topic. I'd like to introduce quality control. And good seismic performance cannot be achieved without good quality control of manufacturing and construction. And every single device must be tested and reported to structural engineers before its installation. And I'd like to show some photos on tests of devices. This photo shows a static test of lateral property of natural rubber bearing. And this photo shows the measurements of some dimensions of isolators. And this photo shows a static test of lateral property of flat sliding bearing. And this photo shows a measurement of some dimensions of the sliding plate. And quality control of construction site is also very important. So accuracy of installation must be inspected and reported on time. And the design clearance between the building and the moat wall must be confirmed after completion. And design clearance between the building and the pipe also must be confirmed after completion. These are also important points to keep buildings function after earthquake. Confirmation of the flexibility of piping and confirmation of the extra length of the electrical wires, are must. This is an example of expansion joints for piping. So it is necessary to confirm that the expansion joint can smoothly move during seismic excitations. And there are many kinds of piping system run through across a building. If a building employs a SI structure, the deformation of each story in the superstructure is relatively small. But at the isolation layer, the deformation will be very large. So we need to use flexible joint as expansion joint. And please imagine a scenario where piping will be added to the seismic isolation layer in the future renovation work. Maybe mechanical engineers will not expect such large deformation. And if the pipe will be filled with some kind of gas, small damage induced by the earthquake might cause explosion accident. So we need to pay attention to not only damage on structural members, but also damage due to moderate earthquakes on non-structural members in the isolation layer. And this is the final slide. This figure shows an example of cost comparison in Japan between non-SI building and SI building. Non-SI building is left and SI building is right. So usually structural cost is slightly reduced by decreasing of lateral seismic force. And repair cost after earthquake is significantly reduced because SI building can protect structure, non-structure, and contents. And as for typical SI cost, it is about 2 to 5% of total initial cost. It is very small increase in comparison with total initial cost. So let's say 10-story office buildings. So structural cost is about 20% of total initial cost. And SI-related cost for 10-story office building is about 10% of structural cost. So SI-related cost is about 20% of total initial cost times 10%. That means 2% of total initial cost. So what if you consider repair cost after earthquake? And SI systems are cost-effective system, especially in earthquake-prone countries. So why don't you choose a SI system? And I'd be very happy if my presentation could be some help to you. Thank you so much for your kind attention.
Give applause for Muramasa. Thank you very much for your advanced knowledge for us. So I open the Q&A session. First, for participant on site, is there any question? Feel free. Okay, Mr. Arianto.
My first question is, yeah, I understand you combine natural rubber bearing with dampers or with the friction pendulum system, yeah, which is you rely on the damping on the dampers, yeah. Okay, sorry. I repeat. So in Japan, you mentioned before that you combine natural rubber with dampers and also with friction pendulum system, yeah, flat sliding bearing, yeah. Yeah, because the natural rubber have a low damping ratio. So you rely on the lead damper. But is it also common in Japan to combine high damper rubber with oil or lead damper, for example? Okay,
Yes.
that's the first one. The second one is you mentioned also before you mentioned that in the building law 2000, I think in Japan, so you should use the response velocity is around 80. So it means that the load for long period structure also have a minimum forces in Japan. Okay, thank you.
So about the first question, so let's think this type of combination. So some buildings adopt high damping rubber bearings plus oil damper. It is also common practice in Japan. And second question, I think is it okay for first question in your, okay? No?
For that, what the purpose? For the first one, not we can understand it because maybe natural building have low damping, but for high damping and lead dampers, oil damper, why there's any purpose for?
It depends on the required performance.
Okay.
Yeah.
Okay, thank you.
And second question is, I think you mentioned this one, I think. So in Japan, we need to design this this response spectrum, and in this black dashed line for not only for SI buildings but also for high-rise buildings. So it's mandatory for newly constructed building.
Okay, so there's a minimum load, yeah?
Yeah, almost same load.
Same for
this is a velocity. So actually seismic force is reduced because the acceleration is decreasing.
Yeah.
Yeah, depend on the period, but velocity is the same. This is a spectrum.
Okay.
For mandatory spectrum. Okay.
Okay, thank you.
Okay, thank you very much, Mr. Aris. Is there any question from the on-site? If not, I will move to the online. Is there any person from the participant from online want to ask directly to our speaker right now? Not yet. How about in the chat room, Mr. Valdi? Is there any question? I believe there is one question in the chat room. Can you show it? Okay, this one is from Eva 567. I don't know. The question is, does the placement of damping system in the design of an asymmetrical building can reduce or eliminate shear walls? Oh, okay. Please, Muhammad Susan.
Yes, you can reduce. I mean, you can place the shear wall or lateral resisting system in an asymmetric, in the superstructure, but you need to arrange the isolators and dampers in isolation layer in considering the balance of lateral stiffness. So is that make sense? Does that make sense? No.
Mrs. Eva, if you have any comment, or is this enough? Okay, let's consider it as enough, probably. Okay, is there any question again from the chat room, Mr. Valdi? Or any of you from the on-site while we waiting for the chat room? Okay, 1, 2, 3, and there is no. If not, I will end this Q&A. Hey, there's another one. Okay. Let's have a look. Our friend still translating the question. That's why it took time. I'm sorry. Okay, this is from Mr. Faiz Sultan again. The question is, in multi-story base isolated buildings, how does the use of passive switching oil dampers influence higher mode effects and potential resonance in the superstructure?
In my basic opinion, multi-story base isolated building. Okay. Passive switching oil damper, the basic properties of passive switching oil damper does not change from ordinary oil damper. It's just changed from the damping properties from lower one to higher one. And higher mode, usually seismic isolation building, the fundamental period of seismic isolation building is much longer the higher mode. So usually we does not need to care about higher mode in the superstructure. So I think, so yeah.
Okay, thank you, Muhammad Susan. So is there any question? If not, okay, that is the last question, and I will end the Q&A session for Muhammad Susan. Thank you very much, Muhammad Susan, for enlightening us. Thank you very much. And now this is the last but not least important. This is presentation. I will introduce Mr. Yusuke Hota. He is Chief Structural Engineer of Mitsubishi Jiso Design Incorporated, and he obtained his master degree from Waseda University. Oh, this is same university with me. So, Senpai, the time is yours.
Thank you for introduction. My name is Yusuke Hotta, structural engineer of Japanese design firm. So today I would like to talk about the recent trend of the tall building design, including some base isolation example. And I would like to talk about this building shown on screen, which is adopting the very unique damping system at the conclusion of, at the final portion of today my presentation. So before starting about the design practice, briefly let me introduce myself. I'm coming from the Tokyo, working at Mitsubishi Jisho Design, which headquarters is locating in Tokyo, and also we have some branch office in Shanghai and Singapore. We have over 800 employees, including over 50 structural engineers, and established in 130 years ago, and it is said one of the oldest architectural engineering design firm in Japan. And our building service is, we are designing all type of the building occupancy. And also we are famous of designing the many tall building in Marunouchi district in front of Tokyo Station. And our recent work includes some big project. This is named Tokyo Torch Tower, expected to be the tallest building in Japan when it is completed in 2028. And also some wood and steel hybrid structure accepting the base isolation system is now under construction in front of the Tokyo Station. And this is also one of our projects. Okay, so let's get back to the topic. So talking about recent practice, I would like to introduce the background of the Japanese performance-based structure design first. So this is some kind of the history of the earthquake record. So, you know, Japan is very earthquake-prone region. So even since after the 20th century, so many earthquake is observed as shown, shown on left side of the history. So in 1923, the Kanto earthquake, and the maximum magnitude is at 7.9, is one of the very famous earthquake in Japan. And since then, every 20 years, 30 years ago, every 20 years, 30 years, Japan observed so many huge earthquakes, larger than magnitude 7. And following this kind, and during the earthquake, many people is injured and many building was collapsed in ancient age. So following this kind of the background, Japanese government issued a building code, launched the building code of first edition in 1950, and the officially the seismic design has been started. However, the seismic regulation is gradually updated, and next big change is the revision of the building code issued in 1981. So compare the building damage observed in the earthquake pre-1981 design and the post-1981 design. The behavior is very different. So this is the damage record tracked out from the report of National Institute of the Research of the Building. This is a record, a damage record in 1980, Miyagi earthquake in 1978. So the whole building is designed based on pre-1981 building design code. So in this situation, many primary structure is damaged and some building is collapsed like this. And this is also the damage record observed in Miyagi earthquake in 1978. So after this earthquake, the design code has been changed. And when we look at the design damage report in 2011 Tohoku earthquake, it is said as far as building is designed based on 1981 revision, the primary structural damage is very minor. However, what is raised at the next issue is non-structural component damage is clarified. So this picture is all observed in observed after the 2011 Tohoku earthquake. So in this case, no structure concrete wall is damaged, and some ceiling of steel structure is falling down. So the people, human life is keep safe. However, people need to evacuate from the buildings. And this is another situation happened after the 2011 earthquake in Tokyo. So the ground motion is very heavy. So people feel kind of the fear, and people try to going back to their own home. Then, however, all trains services suspended and all bus services suspended. And what happened in Tokyo? People is crowded in the station and all traffic is jammed. So after this lesson, what's the trend of our situation is how do we maintain the building function after the earthquake? So no longer keeping the stability of the structure is not enough. So what we are trying is how we keep staying inside the building. Moreover, especially when we design the huge scale of the buildings. So when we talk about the building performance-based design, I think ASC 41 is one of the reference. as shown on this page. However, ASC 41 doesn't show any specific design criteria. So this is just a reference, I think. So what we are typically doing is creating this kind of the matrix, showing the design performance and discussing with the client and determine the building performance which we target for each project. So we are doing this kind of discussion in very early design stage of the project and determine the design criteria. And once client want to improve the building performance, I think there are several options to improve the building performance. So installing the damper is one of the options, and adapting the base isolation system is another option, I think. So even base isolation system, the isolation layer, where the isolation layer is installed is another discussion. So beneath the building or between the story could be the option. So I would like to introduce briefly one example utilizing the base isolation system. So this is the condo apartment building having the over 180-meter tall above grade, having the 48 stories above the grade. So this building is individual owner is gathering apartment and is very interested in the performance under the earthquake. And the building shape is like this. So the longer direction is a 57 meter, and the shorter director is around the 40 meters rectangular shapes. And the residential unit is locating the perimeter of the buildings, and at the center portion, the mechanical parking located in. And how we design the base isolation for this tall building is generally for the condominiums buildings, Japanese is very common to use a concrete structure. So the building superstructure is designed based on the moment frame with a core wall locating at the center of the building. And I think there are some questions from audience whether which type of the moment frame I accept. Unfortunately, in Japanese code, there is no grouping of the moment frame system. And when we say moment frame system, it's a one system. And I think it's very close to the special moment frame in ASC 7. And this is a component of the base isolation layer beneath the basement one. So the isolation layer, isolation device is used LRV and the oil damper, and blue one is LRB. And the yellow cylinder shows the oil damper. The LRB is installed beneath each columns, and the maximum size is a 1,500 millimeter square, and capable to carry the over 4,000 tons of the gravity load. And why we install the additional oil damper is considering the long duration time earthquake. So as far as using the metal damper, we are afraid about the fatigue issue with unexpected ground motions. So, however, oil damper is very durable damper device. So why I choose install the oil damper is it's kind of the additional reliable damper devices. And the next page shows the performance comparison between conventional concrete moment frame versus base isolation system adapted this project. So the numerical simulation is run using the Great Kobe earthquake record in 1995. And as you can see, the behavior under the earthquake is very different each other. And this one is also the numerical analysis simulating the behavior inside of the rooms. So now you're watching the behavior inside the residential unit of 48th story. And another one is simulating the base isolated case. So as you can see, the floor acceleration response is very different each other. So the behavior inside the room is very different, even though this is the high rise. Because when we design the conventional concrete structure, the fundamental period is around the 4 seconds to 4.5 seconds. However, installing the base isolation, the fundamental period under the earthquake is longer, reached to around the 6 seconds or around some. That's why we can further mitigate the acceleration using the base isolation devices, even if it is the high-rise building. And this is the picture of the LRB device which we use for this project. And also, precast concrete method is adapted to accelerate the construction duration time. So this is another picture. So the column is manufactured in the factory, and the beam column connection is also manufactured in the factory. And what we are doing is assembling the piece and filling the grouting and fix the primary structure elements. So core wall is also using the precast method like this, and every typical floor is constructed in 5.5 days in average. So I understand the base isolation is very super helpful tool to improve the building performance. However, base isolation choose the building types. So for instance, if the building has this kind of the stepped garden or sunken garden, how we install the base isolation layer in the building. So as a committee member of the JSSI, I would like to recommend using the base isolation as much as possible. However, in some case, base isolation structure is not the best choice. So for such a situation, I think damper control structure could be the alternative option. So when we design the damper control the structure, the simplest way is just adding the damper as shown on here. So in Japan, there are so many types of the dampers. So this one is the kind of the viscous damper. The viscous material is filled between the steel and the wall type damper. And this is very common oil damper. And BRB, a buckling resisting brace, is also acting as a damper if the low yielding buckling brace is accepted in the building. And so, and as far as installing this kind of the devices only, the damper control structure system doesn't choose the building overall shapes. So as I introduced at the beginning of today's presentation, more than 95% or more than 99% tall building in Marunouchi adopt this kind of damper control frame system and improving the building performance under the severe earthquake. And also this system can be applied to existing buildings So this is one of our case. The building is completed original building is completed in 1980 or somewhere around that. And the total building height is 240 meters above grade. But after the building completion, the design code is slightly changed, and the building doesn't meet the latest design code. So clients decide to reinforce the building using the damper devices, as Muramatsu-san introduced at the previous presentation. So in this case, applying some additional oil damper and additional low yielding steel damper, then improving the building performance under the earthquake. And now the building performance is close to the latest building regulation. So damper control structure system is very flexible and useful, as well as a base isolation system. But what the problem or what the point which we need further improvement for damper control device system is this. So what's the principle of damper control structure system is how we dissipate the seismic input energy. So generally, seismic input energy is dissipated by natural damping of the building and frame yielding energy dissipation, plus damper energy dissipation. So as far as this damper energy dissipation is working efficiently, we can reduce the energy dissipation due to the frame yielding, meaning frame keep elastic even after the severe earthquakes. So how we design the efficient damper is one of the key topic which we recently discussed again and again. So just installing the simple damper devices is just expecting the story drift of single stories. So let's imagine if we target the 1% story drift under the severe earthquake and considering about the 4-meter height office building, the story drift under the earthquake is just a 4 millimeter or around some, 4 centimeter or around some. So it's very tiny movement. So even though even for creating the very good damper, the energy dissipation provided by damper is very limited. So from now, I would like to talk about the Tamachi Tower, which I recently designed. It's accepting the different, some special system to improve the damper energy dissipation. So before talking about the structure system, let me talk about the outline of the Tamachi Tower in advance. So Tamachi Tower is the steel moment frame buildings locating in nearby Tokyo Station. And the building height is 156 meters above grade. So building site is just 8 minutes train ride from Tokyo Station and approximately 40 minutes train ride to Haneda Airport. So it's very convenient location. However, recently, Tokyo's office market is very competitive. So clients want to improve the building performance as much as possible to attract their tenant to would like to coming into the buildings. And so lower level of the building is very open to public. At the level 2, there is a pedestrian deck is arranged. And at the level 1, we have some greenery space. And from the level 1 to basement 2, we have the sunken garden, which I shown previously, and directly connected to the subway station. And also at the lower level, we have some retail, meaning the non-business occupancy, respecting for the town planning master plans. And office entrance is locating at level 2. So office entrance is locating at level 2. And building shape is like this. So above level 2, we called it, above level 6, we called it typical floor. So typical for plan shape is almost square, and the shorter length is 58 meter, and the longer length is 67 meter. And the office core is locates almost center of the building, where I put the red cover like this. So what I do for this building, I would like to talk. So as I mentioned, at the very early stage, I discussed with the client regarding the targeting building performance. Sorry about that, letter is very small. So this matrix shows the earthquake scale on this line. So minor earthquake, moderate earthquake, large earthquake, and ultimate large earthquake. So based on Japanese building codes is only mentioning lower level than this large earthquake, roughly say, let's say level 2 earthquake. And level 2 earthquake is said mean expected return period is around 500 years. Generally, under this level 2 earthquake, most high-rise building, recent high-rise building, is controlling the story drift less than 1%. The maximum story drift is less than 1%. And some project controlling the ductility factor as well. So this is the normal line of the recent tall buildings. And it is said after the level 2 earthquake, building can keep standing. However, we might need some repair for continuous use. So what we aim to this building is scale the level 2 earthquake to 150% amplified, considering the 150% amplified level 2 earthquake, and targeting the same criteria with the ordinary level 2 earthquake. So it's meaning considering the 150% earthquake, and the allowable maximum story drift is just 1%. In this case, maybe we can say even after the level 2 earthquake, the building damage is very minor, and the client and the tenant can keep staying inside the building, and then the required maintenance or repair is very limited. But the criteria has been determined, but how we achieve this criteria is the next problem. So in such a situation, I looking back at the building component. So this is a building component of the Tamachi Tower. Above level 6 is the office, and below level 6 is without outside other of office occupancy. So when we think about the people flow of the office worker is coming from the train station and climbing up to the level 2 and riding on their elevator and directly pass through above level 6. So between level basement towards level 4 or level 5, the office core is kind of the void for the building. overall buildings. So very easy to close and easy to reinforce. So using this method, please see the right side picture first. I replace the office core below level 6 to concrete core, and above level 6, overall structure is designed with a steel moment frame. And between level 1 through level 6, the frame surrounding the concrete core is designed by steel moment frame. Additionally, the concrete core, beneath the concrete core, we applied flat type slide bearings. So what's happened in this component shown on movie on left side. So concrete core is much stiffer than the steel moment frame. So considering the 1% story drift under the levels 2 earthquake or more severe earthquake, the steel moment frame is deforming 1% each story. So if level 6 locate the 30 meter above the grade, that's the movement at the level 6 floor is around 30 centimeter. However, sliding concrete core is moving very rigidly. So what's happened in this situation? Very big differential lateral movement happened below level 1, as this movie shows. So using this big amplified differential movement, I installed a damper device between the concrete core and surrounding steel moment frame, and maximizing the energy dissipation due to the dampers. So this is a detailed drawing where at the top of sliding core and the bottom of sliding core. So left side is the top of sliding core. So as you can see, steel moment frame is connecting to the concrete core wall system. However, at the level 5, we have the clearance here. And look at the bottom of sliding core. The yellow portion is the sliding core, and the blue portion is the outside frame. So the corridor of basement 2 is designed with a cantilever slab, and we have the maximum 30 centimeter clearance here. So the sliding core can move left and right under the earthquake, and the installed damper can dissipate the energy during the earthquake. So this is the device picture. The left side is sliding low friction slide bearing, which we used. Maximum size is 1400 square at the rubber portion, and designing the maximum 30 centimeter horizontal movement in 2 directions. So this steel plate size is over 2 meters, and the rubber portion is 1.4 meters square or 1.5 meters square, and carrying the over 4,000 tons. And this is the viscous damper imported from the US. And this is a plan drawing indicating the number of the slide bearing and the viscous dampers. We used 24 viscous dampers and 10 slide bearing in total. So what's the unique point of this structure system is 2 different movements happened in one buildings. So design for the clearance need to be very careful. So the maximum clearance required is 30 centimeters. So as you can see, the blue portion, this portion is the slide concrete core, and this here is the corridor outside of the core. So we applied the additional dry partition wall and hide the clearance to avoid the people falling down. and locate some MAP shaft around the sliding concrete core. So this is a picture looking over the clearance. And this one is a picture seeing toward the viscous damper connecting sliding core and the surrounding concrete system. And as you can see, some scratch plate to observe the movement under the earthquake is installed, shot like this. And so this system is hybrid of the damper control system and the base isolation system. So MAP piping detail is following the guideline of the base isolation system issued by JSSI. And this is another picture showing the clearance. Left side is a concrete wall, and right side is a dry partition wall. And another picture here. And another picture here. This is me. So maybe you can feel the scale of the pit. It's very huge scale because elevator is coming down. So in order to secure the enough height of the elevator pit, naturally the bearing footing beam of the sliding core gonna be over 2.5 meters or more. So again, what's the concept of this damper control system is utilizing the sliding crown and maximize the energy dissipation due to the damper. So, and this is some narrative indicated to the client at the very early design stage. So we quickly run the comparison comparative numerical analysis. So left side is a conventional damper control system, and right side is the proposed damper system. And this one shows the numerical response result. So how long I have? 5 minutes. Okay. So the black line is the conventional damper control system, and the red line is the proposed one. And for reference, this one is an intermediate story base isolated structure system. So what we can see here is we can achieve the similar performance above level 6 between base isolation system and this proposed system. However, when client look at this diagram, client says the building performance is already improved. So let's use this system to reduce the cost. So finally, we optimize the number of the damper, and this is the final result under the level 3 earthquake, meaning the 150% amplified level 2 earthquake. So sliding core is moving 30 centimeters as we expected, and the maximum story drift is 1%. And sliding core devices dissipating the 35% of the overall seismic input energy. And this is a comparison of the cost saving. So due to replacing the steel moment frame to concrete core and reducing the number of the damper, the steel tonnage is slightly reduced. And also the number of damper is dramatically reduced. And finally, we can succeed in saying 5% cost saving, accepting this structure system. And also, installing the damper is a kind of the space eater. So reducing the damper means we can get the additional buffer for the floor space. So following the squeezed core, we can apply this kind of the well-being facility for the tenants. and make client very happy. Okay, so this is last page of my presentation. So thank you for listening.
Thank you very much, Hotta-san. And now I will open the Q&A session. Is there any question from the participant on site? Anyone? How about from the online participant? Is there any question? You can ask directly. Or is there any in the chat room, Mr. Faldi? We have one. Okay, you can share in the Zoom. Yes, this one is from Mr. Gambiro. His question is, for a building that use base isolation, should the structural system be ductile or non-ductile? Please, Atas.
So when we design the base isolation system, generally building frame, superstructure frame should be keep elastic. So as for the potential of the superstructure, it's very ductile frame. We designed a very ductile frame, but based on the calculation, we don't observing any yielding hinge in the superstructure.
I see. Okay, we move to the second question. In a building that use a combined frame and core wall system, where the frame is supported by base isolation, can the core wall also be supported by base isolation? Oh, I see.
I see. Sorry about the confusing explanation. So core wall is supported by base isolation, and other of core wall is touching on the ground. So no base isolation device is installed.
That explain much, many information. Mr. Gambiro, is there any question again? Mr. Faldi? Or from on-site participant? Please feel free. Mr. Faldi, still? One more? Okay. They are still translating the question. Sorry. Nah, there is one more from Mr. Faiz Sultan. In your presentation, you mentioned about beyond code requirement. In your practical experience, what type of buildings, for example, hospital, data center, emergency operation center, most frequently require seismic performance targets beyond code requirement? And what are the main technical reasons for adopting beyond code design in these cases? Wow.
It's a very good question. If today it was 10 years ago, only hospital or government facility is requiring the beyond the code requirements. However, recently, even if the owner of the tenant building is very interested in upgrading the building performance, because gradually the number of upgrading building is increasing. So in order to invite the tenant easily, building should be competitive. So recently, every owner is at least one time talking about beyond the code requirement.
Super. So, is there any? Okay, we have two more questions. Okay, please, Mr. Faldi, from Mr. Karis Maulana, UMB. If a building is constructed on a hill with different level of restraint and a length to width ratio of approximately 1.5, what type of seismic isolation system would you recommend, and what should be considered in terms of design and implementation? Oh, on a hill.
It's very, I think this is some practical project exists. It's very unknowable case. So when we design the base isolation system, we first we check the surrenderness ratio. And this is just my individual opinion. If the surrenderness ratio is over 4, it's very tough to design the base isolation system. So in this case, Christian people is trying to design the surrenderness ratio 5.5 buildings. So in this case, we need be very careful for the tensile force induced by the building overturning moment. And they also need to care about the ductility of the base isolation layers. And also, we need to take care of the wind. So under the wind, in Japanese case, we don't allow any yielding for the dampers. However, when the surrenderness ratio is raised over the surrenderness ratio 4, the transverse direction, wind transverse direction response getting higher than the wind load direction. So sometimes the damper capacity is determined by that kind of the wind response. So, so the primary advice to this question is let's lower than the surrenderness ratio. How do you think of this about?
So, I'm afraid I think this is a I think this is a building with a length to width ratio of approximately 1 to 5.5. So I think this is a kind of very wide length buildings. So I think this yeah, your comment is right for taller building. I think this is a kind of low building with a rectangular shape. And so the torsional effect is you need to much pay attention to torsional effect, like accidental torsion, because the weight of building it's different from the calculation of design calculation. So you need to consider the happening accidental torsion in actual situation.
Okay, I think that's enough. So we still have last question. One more from Mr. Charles Priyanjaya. Question is, when the base level of the building is not in the same elevation, sunken or hillside structure, where is the base or recommendation location to put the base isolation? Is it at the lower base level or at the higher base level?
So generally, the isolation layer level should be flat as much as possible. But I understand some restriction. We need to design the stepped base isolation layer. So which is the best? It is, I guess, depend on the size, plenary size of the lower portion and the higher portion. If the lower portion is, for instance, just the elevator pit or small portion, arranging the base isolation layer at the higher level, and the lower portion is suspended from the higher portion is one of the options, I guess. And if the lower portion is the major, the base isolation layer is designed based on the lower portion, and higher portion is, for instance, a cantilevering from the major portion or applying some support secondary devices, such as sliding pot or some small devices.
Probably Muramatsu-san, you want to add? No?
I'm totally agree with Hotta-san.
Okay, so it's clear? Only that, Mr. Faldi? Okay, I will give one more chance for the participant on site. Is there any question? I see. Okay,
Thank you for the nice presentation, Mr. Yasuke. I have question about applying the base isolations in the high-rise building. As I know, we have in ASCE 7, we have to make the natural period of the fixed base structure is 3 times than the isolated structure. So if we want to apply the base isolation to the high-rise building, it means that we have to make the structure is very stiff. Is it effective to apply the base isolation to the high-rise building? Because as we know that the natural period is already a long period. Thank you.
Thank you for the question. So, looking into the Japanese code, we don't have any mandatory regarding the fundamental period expansion. However, as you mentioned, if the high-rise building has the naturally long building period, the building itself has already had the kind of the mitigation of the earthquake load. However, so that's kind of the argument is happened even in Japan 10 years ago or 15 years ago. And many engineers tested the model cases. And the conclusion is that effectiveness is slightly minor compared to the lower buildings. However, we can have more or less benefit utilizing the base isolation base isolation for high-rise building. But in order to optimize the base isolation device effect, the rigid superstructure is preferable. So what I do on my project is inviting the concrete core wall inside of the building. So Japanese building is typically designed with a moment frame, but we can find some portion we can install the concrete wall. So when we design the high-rise building, base isolated high-rise building, we look for the portion where we can apply some kind of concrete wall or additional post to reinforce the superstructure stiffness. Is it meet your question?
Yeah, thank you.
Okay, thank you. But you forgot to mention your name, sir.
Oh, sorry. My name is Josia Rastandi.
Okay, thank you very much, Mr. Kasandi. Is there any question? Last chance. Okay, if no question from on-site and online, I think that's conclude our morning session today. And so thank you very much, Saito Sensei and Muramatsu-san and Hotta-san. Thank you very much for your presentation and all your knowledge that being shared to us, and that will be very useful for us today and also to the future. I hope we will meet again and we can share again with the participant another time. Okay, thank you very much, ladies and gentlemen. Let's give applause for all of us. And that is the end of this session. I will go back to the MC, Miss Hawa. Thank you very much.
Thank you for the incredible presentation from the speakers. And the next agenda is the certificate handover from our Okay, the next agenda is break, and all the participant is pleased to enjoy the food and expected to be back at 13:25. Thank you. Distinguished participants, thank you for your willingness to stay in this event. We will continue our presentation. In this session, we will be led by Mr. Eka Ciptawiguna, STMT as moderator. To Mr. Eka Ciptawiguna, STMT, the time is yours.
Good afternoon, ladies and gentlemen. We will continue to our second session this afternoon, but unfortunately, I need to inform you that Mr. Tomohiro Inoue cannot join us in today's presentation because he's fallen sick. So we will have two presentations this afternoon. Let me invite Pak Aris Arianto from Institut Teknologi Bandung and Pak Felix Hotama from Magdatama Multi Industry. So in this afternoon session, Pak Aris Arianto will share about the application of seismic isolation in Indonesia, and Pak Felix Utama will share about LRB testing and production per EN 15129 based on Magdatama experience. Okay, I think all of us is ready. So I will give the time to Pak Aris to present his presentation.
Okay, good afternoon, everyone. Thank you for attending this session, and also thank you for Pak Eka to introduce me. So my presentation title is about the seismic-based isolation application in Indonesia. I will talk about the concept and design, also design code, and also some example applications of the seismic-based isolation in Indonesia. Okay, this is the outline of my presentation. First, we will talk about the concept of seismic isolation. Maybe before also, before presenter also mentioned about that. Maybe I will highlight several things also, and then I will talk about the design procedure based on the Indonesian standard or AAC standard, and the example of application seismic isolation in building and bridge in Indonesia, and also some future our research development, what we do in our campus in ITB, research on seismic isolation. Okay, so the basic concept of seismic isolation is, as mentioned before also, is to separate the upper structure with the ground motion on the ground, caused by earthquake. So the best thing, if we want to, of course, if we want to separate those two components, we should levitate the building or flying the building, so there's no contact anymore with the ground. But of course, it's very difficult and uh, uh, not efficient. So base isolation or seismic isolation is used in this case, yeah, because they have a flexibility element. So we introduce the flexibility element or base isolation. So the structure will, yeah, in some part can be like decoupling or separating. So the most of the deformation primarily occur at the base of the structure, and the upper structure not accelerate or not deform largely. So that's the main concept of seismic isolation. And also, yeah, of course, when we reduce when introduce the seismic isolation, they will reduce the seismic force due to the extent of structural period and also the damping. One also that why we use the seismic isolation is there is still some misconception or misunderstanding for building owner when, for example, when we design structure, a seismic resistant mean that structure will be safe or will be function after earthquake. But that's not true, because our design code, if we design the building under code compliance, most of building, office or residency building, the performance level is life safety. It means that the structure will experience damage, extensive damage, but not collapse. So that's different expectation between designer and maybe for building owner mostly. Except for, of course, for like important structure, yeah, we introduce also for on levels immediate occupancy or full functional, but we introduce the enforcement factor for that. So this is also why we use the seismic isolation. So seismic isolation, we want to increase the performance level of the building, not only have a life safety, but also the building have more economical after earthquake, no repairing, for example, and also no damage on the non-structural or mechanical electrical components. That's the main reasons. Yeah, as you can see here, in this slide. So for ordinary building like office or residential building, the performance level under design earthquake or maximum earthquake, like 10% of in 50 years or 500 years, or 2% for 5 years or 2,500 years written period. So the building is designed mostly under life safety and collapse prevention, which means yeah, they have extensive damage. But if we move to the operational and immediate occupancy for this building with conventional method, yeah, it will be costly, expensive, and also difficult, because we should enlarge the column, enlarge the element, or adding more shear wall and more other structural elements. So may reduce the capacity of the building. So this is also why we introduced the seismic isolation. And in this table also showing that the possibility the isolation can minimize or prevent the damage on the structural and non-structural under moderate and major earthquake. And the other the other reason is also that the base isolation also can reduce the floor acceleration. So if we have the sensitive building, for example, like a data center or laboratory equipment, we can also prevent for protecting those element or those component by introducing the isolated system. And also for, like I mentioned before, that when we introduce the when we reduce the floor acceleration, the comfort of the occupants in the building during earthquake also will be reduced. So the comfort will be increasing. So we not have a motion sickness or something like that. So this is the main also the main reason for the introducing the seismic isolation. There is some criteria, important criteria when we choose the seismic-based isolation system. The first thing is the seismic isolation system has should has flexibility in horizontally but stiff vertically. Because why we should have a stiff in vertically? Because most of the seismic isolation is support the columns and also located in the base. So the vertical load will be large. So we should design the isolation have a stiff vertically, so they cannot experience damage or bulging like under vertical load. And the second is the seismic isolation system also should have excellent dissipation capacity. So it means that the seismic isolation should has damping, significant damping to restore the seismic force to the original position, for example, and also dissipate the energy of the seismic. Because if we not have the excellent dissipation, maybe the structure will be moved uncontrolled. So this dissipation capacity will prevent for that deformation. And the third one is the seismic isolation also should have restraining or stiffening against the frequent wind loading and frequent earthquake. So when the wind coming and or the frequent earthquake coming, the system is still stiff and the people's the comfort and not but under large earthquake the system seismic system work and work to reduce the force. That's the second thing. And the last thing is the seismic isolation also should have the durability or the performance level under deterioration. Yeah, because we know that we put this isolation system within the lifetime of the building. So we should, the isolation system have the minimum aging deterioration, for example, under temperature or under environmental, that we should also have criteria. So this is the types of the seismic isolation that maybe mentioned before. I will explain some differences. For example, for natural rubber bearing, they behave they have a linear elastic behavior, which is have a good stable restoring force, but it has mostly has a small damping factors about 2%. So to to increase that, some we should some stopper or damper to minimize, to increase the damping. But this natural rubber bearing is easy to manufacture and have a reliable performance under aging, creep, or temperature. So this is the second thing is we have also lead rubber bearing. So the difference is they put a lead core in the center of the rubber. So this lead core provides additional damping and vertical stiffness to sustain the gravity load. So mostly this LRB used for bridge, for example. And this lead core also, like mentioned before, that govern the damping. So for larger lead core, produce the larger damping, but also produce a higher stiffness. So we should optimize the dimension of lead core to have flexibility and also the stiffness. And this lead rubber bearing has have a quite effective damping large, around 30% up to maybe 40%. And also the distinction between the natural rubber bearing, they have a bilinear relationship. So they have a yielding point. The third types is the high damper rubber bearing. It has damping around 15 to 50%, because we add additional compound on the rubber. And also the trees, they have a high shear strength level, mostly more than 120%. So they will have a good damping based on the because they have a higher shear modulus. And also in the higher shear strength, they have a stiffening effect. So the bearing have increased the stiffness. And the last type of here is the sorry, maybe not light bearing, but the friction sliding bearing. The main of this system is they have the friction due to we put the in the surface, and also they have a restoring force due to the geometry, because like a pendulum, they can come back to its original position, and we can modify the damping based on the radius of the friction, the pendulums. So this is also have high performance for seismic isolation. Okay, in addition to that types, and also there's some general practice when we design seismic isolation. First, there's the seismic isolation have a significant improvement in seismic performance, especially for short period and low medium rise building. But yeah, as mentioned by previous speaker, that in high rise building or long period building, there is some also system that can also good when using the seismic isolation. And when we design, the base floor issues should rigid enough to prevent differential lateral movement. So we should have a precaution for soft soil. So because when we have a soft soil, when we increase the further, the acceleration also can increase. So we can have a benefit for the seismic isolation. So that is also should be considered in design. And also, yeah, to preventing uplift, we should have the weight, have enough weight to balance the overturning moment, and also, yeah, we should considering the uplift forces by like mentioned before that we have the aspect ratio in Japan. A rule of thumb is 4, yeah, the aspect ratio, but it's not. I mean, the fix. We can't also explore run if we want to above that. And also, when we design the seismic isolation, we have enough space or gap that structure can move freely. Yeah, we should consider that the gap to provide the displacement during the earthquake, and also the some non-structural element like stair, like a wall, or some kind like expansion joint, like mentioned before, also should have move freely, so they cannot resist the or pounding when building is moved. And also, yeah, we should consider the structural or non like a mechanical element, not yeah, have a special utility like flexible joint and so on. So this mechanical electrical system also still working, because if yeah, maybe building is okay, but not. But if we have not flexible, not a good utility system, yeah, the building maybe not function anymore. Yeah, so it's also is important to consider when design. Yeah, as mentioned before, there's some yeah, mistake when in Indonesia, yeah, when have in terms of the mechanical electrical system when we use the seismic isolation. And also when design, yeah, not all engineer knows how to design. So yeah, we need to increase our knowledge to how to design properly using the seismic isolation. And also when installation, yeah, we should consider very detail, yeah, because we should put the seismic isolation in the flat, maybe yeah, minimum is the flatness. If we have not flatness, so there's some effect on the isolation bearing. And also the alta effect also we need to consider, because when those structure moving, there is some eccentricity on the structural element above or below the base isolation. So we should also considering that when we design. This one also important. So some designer might be forget about that. So I think the field effect also we need to consider during the design seismic isolation. Okay, that's all for the yeah, basic concept or when designing the seismic isolation. Let's move to the how in Indonesian standard for designing the seismic isolation. In Indonesia, we have for design and the seismic isolation, we have SNI 1726. The seismic based isolation system firstly introduced in SNI 1726 2012, yeah, which is mostly adopted from ACE 2010. and also and then revise and then we update into SNI 1726 2019. There's follow the ACE 716. There is some differences in these two updating. Mostly in 2019, we should design based on the MCR, yeah, not the basic the design code, but and then also one thing is about the property of the installation. We should consider upper and lower bound property. That's the main difference between last SNI to the new SNI. In SNI, the seismic installation system, the philosophy of design, yeah, is I already mentioned that the system, this SNI is not specific for new for one type of the seismic installation. It has only give a general standard design for many types of installation systems. So in SNI is a general concept. So in this SNI also mentioned some general philosophies like should maintain horizontal accidental stability, have a restoring force, and also have a good performance, not and under repeated cyclically not degrade, and also all parameters should be quantifiable. So should be tested, for example. That's the main philosophy for when designing the seismic system based on SNI. In SNI, we have 8 chapters. So if we grouping, we have into 5 group, like the general design requirement, and then seismic ground motion criteria, analysis procedure, design review, and testing. That's our SNI covers in for designing seismic installation. In general design requirement, for example, for important factor, we use always one. And for redundancy factors, we can use rho is equal 1 if no irregularity. Yeah, but for irregular, we can see section 17 for ICE. And for requirement for installation system, first one is, yeah, you should have required for resist wind load before the seismic installation, have also good performance for fire resistant, and have minimum lateral force, and also uplift and overturning should not exist except for if we consider it. And also we should evaluate lower and upper bound condition of isolation system. Yeah, the property we should consider, and also during the inspection and replacement. For the structural system, some general design requirement is for horizontal distributed force. So we should have the horizontal diaphragm or other element that provide continuity above the installation system. And then also have a minimum building separation, based on not less than the maximum displacement. And also we should consider different action or different forces for component above and below the installation system. This is also important thing, that we should design different forces between upper structure and structure below the installation system or installation system itself. And also for the vertical load combination, we should consider average, minimum, and maximum vertical load. For average, we should consider live load, and for maximum and minimum, the SDS should be replaced the SMS because we use MCR. Okay, and then for the property modification factor, yeah, as mentioned before, that we should consider upper and lower bound property of the isolation system. If in this case, we should ask the producer of the installation how the factor for the installation, the like edging effect, heating rate, length, and so on. So we can calculate the maximum factor and minimum factor or upper or lower bound property. We can also use when we test it on the full scale prototype specimen, we can also using those data when we using for property modification. But if not, we can use this equation. And for installation system, also we should consider the effective stiffness and effective damping based on upper and lower bound. Yeah, you can see in the figure we have maybe two loops. Yeah, the upper loop is upper bound, which has higher stiffness, and the lower loop is the lower bound, which is the lower stiffness. Mostly when we design, the upper bound mostly govern for selecting the structural dimension, and for lower bound mostly we can use for selecting the isolation dimension or displacement. That's govern on those two parameters. And for the seismic ground motion criteria, we should consider which seismic hazard that all seismic load that we consider. For if we use the site seismic hazard, if we have several criteria, for example, if the site is S1 greater than or equal to 0.5 or have a site class E, D, or F, so we should make a site specific seismic hazard. Or also maybe if we have a near fault, also maybe a site specific seismic hazard is also should be considered. But for analysis, for which seismic hazard that we use for ELF and response spectrum analysis, we can use the MCR response spectrum. But for response history analysis, we should use the MCR ground motion. Minimum is 7 pairs, and also should be selected and scale for of the magnitude and based on the magnitude, fall distance, and source mechanism. For the analysis procedure, here we have static and dynamic. For static, we have equivalent lateral force procedure. Yeah, of course, not all the system can use the equivalent lateral force. There's some limitation if we want to use equivalent lateral force, like mentioned here, like for site class, effective period and a number of story, for example, and also the irregularity. But still, when also we design the dynamic in using the dynamic procedure, the static procedure should be also calculated, because we should compare between the dynamic forces to equivalent forces. For dynamic procedure, we have two types: response spectrum analysis procedure and response history analysis procedure, which is the most comprehensive one. For equivalent lateral forces procedure, mostly we consider as structure as a single degree of freedoms, and we assume that the isolation is linear elastic behavior, but we know that not all the isolation have a linear elastic behavior, yeah, but we use the effective stiffness and effective damping of nonlinear isolator. And also the procedure is iterative, and yeah, this also can be used as the initial for design, yeah. And here, yeah, some differences between SNI 2012 and SNI 2019. The vertical distribution is quite different. And 2019 more realistic because the lateral forces mostly not like a triangle, yeah. And yeah, the forces, as I mentioned before, that also we have 3 lateral forces that we should consider. VB, like the total lateral seismic designed for for isolation and for element below the base isolation. So they're governed by stiffness, effective stiffness and damping of the isolation. And also for the upper sector, we use the total reduced lateral seismic descent for VS, yeah. Maximum we have the R is 2, yeah, in our code. And also we have the VSD with this the unreduced lateral seismic or element above percent, which is mostly is used for the calculating the overturning moment. So we have 3 types of the shear forces that we should design properly. Yeah. And also we have some limit on VAs. Yeah, first, yeah, seismic should be larger than the fixed structure with the effective period of a solar system using upper bound properties, and also should larger than the factor design wind load, and also for the VST should be equal to VB or have some properties criteria of there. And for the response factor analysis, we should design in 3D model. And we also use the hybrid response factor, means that we have to curve, yeah, the curve with the damping 5% and the curve after T effective with damping with isolation sector. That we should use this hybrid to calculate the shear and response of the sector. And also we assume the linear elastic behavior of the isolation system, which is not true, because we have mostly yeah, by using the effective stiffness and effective damping. And also this procedure, also the iterative calculation. And yeah, the most sophisticated analysis is the response history analysis. As mentioned before, we should select it the ground motion, yeah, based on the location. So the magnitude, the yes, here we have SNI 8899 2010 to select the ground motion that fit with our location. And also we should model the nonlinear behavior of isolator under upper and lower bound forces or deflection properties. And yeah, for the displacement and forces, yeah, there's some we should limit, or we should if we use the spectrum analysis or time history analysis, we should limit our lateral forces. For example, for response spectrum analysis should be not less than the story shear or shear force from the VB, yeah, means from the static analysis. And for the response time analysis, we can use the VB is not less than 80% if a regular structure, but if irregular structure, we have 100%. So this is why we should still calculate the static or ELF response, ELF seismic pulse. And also the maximum story drift is different, yeah, for response spectrum analysis. The maximum story is 1.5%, and for time history analysis is for 2%. That's the maximum drift limit. And also in our SNI, we when we design the seismic building with seismic isolation, should be reviewed by independent design review. Maybe we have a TPA or KKJTJ with one or more individuals. Yeah, this criteria, what we should review, you can see in this, which one we should review. Well, why we should review of design? Because first is this isolation system is not common for most engineers, so we need to review. And also some product may be different also for many system, yeah. And also we should testing the isolation should be qualified for maybe prototype testing, maybe to full set specimens. And yeah, because of, I mentioned before that because each producer of the isolation have different materials, different properties, and also maybe different contraction method. So we should test it and prove it that the isolation have a good performance. Okay, that's the design procedure based on the SNI or ACA 7. Here I will showing some example application in seismic isolation in Indonesia. Maybe this is the first one, yeah. The seismic isolation using the building has using the seismic isolation, yeah. It designed by David Sukamta, Pak Eka. Yeah, the Gedangan office has 24 and 2 basement. They use high damper rubber bearing. Number is 40 points, yeah. The period structure we fix is 1.6, shifting to 4.2 seconds, yeah. And on those cases, maybe we don't have any, because the design, as mentioned, is Davi Sukamta mentioned that 2009, maybe, yeah, this is 2020 is completed. Maybe we don't have an code using this bidding, yeah. And yeah, using SCA 7 2005, yeah. Okay, so this is like the section and the plan of the building. Because it's quite high rise building is because David Sukamta put some core wall and outrigger to stiffen the structures and to spread the load, yeah. The base isolation put in the basement, I think, yeah. Okay, this is the location of the isolation system using Bridgestone high damping rubber bearing. Okay, and this is the result from analysis. So they compare with the fixed structure, which are 6 and CD5. Yeah, the deformation is below. This is below 0.5%. Yeah, I think mostly 0.2% is very good story drift. Yeah. This and then another building that using seismic isolation is Grand Eastern City Hall in Medan. Is completed 2010 using also high damper bearing. So this is also using the old design, yeah, maybe using design seismic load, yeah. Now this is the new ones in Wika Tower in Cawang. This is also high damper rubber bearing, have 70 floors, and shifting the period from 2 to 4 seconds. This one is already used the SNI 7026 to 2012, yeah. The difference in this building, they put the seismic isolation not in the base, but in the ground, between ground and upper ground. So you can see here, and also, yeah, because they put in the between ground and upper levels, so they should stiffen the beam, yeah. So by putting the stiff beam on the below the column to ensure the rigid diaphragm action on the base isolation. Okay, and then yeah, this is the new ones, the PMKG building. Yeah, maybe visited by JSSI. This is have a different isolation system, yeah, friction pendulum system. They have 23 points. The shifting period is from 1 second to 3 seconds. Okay, and but it's still using the 2012, yeah, no, 2012 or new one, new one, yeah, 2019, yeah, already. So using MCR, yeah. Okay, that's all example seismic isolation in the building. This is example in the bridge. In the bridge we have LRT. They use lead rubber bearing, yeah, built in 2015 and 2012. Yeah, we have 43 kilometer late viaduct. The soil condition is soft to medium soils, and the design code still using 2830 2000 using the still 500 years, yeah, and updated, but in using the written period 100 years. So when they update it, so they introduce the this rubber bearing. In our design code, we in bridge, we still don't have SNI to 833. We still consider the seismic isolation, I think. So we still using the ASTO GSID 2014. Okay, this is the bearing type that used in this project, and also the performance, yeah, the maximum displacement and also forces. Yeah. Okay, this is the checking for the LRB deformation. Yeah, still under capacity displacement. Yeah. Okay, and also the Jakarta Cikampek elevated Indonesia also using bridge, yeah, using elevated bridge using LRB, yeah. Yes, yeah, design using the written period 100 years and also still using ASTO GSID for designing. Yeah, this is showing the shifting period, yeah, the structure mostly around 1 second and move to 2.2 seconds, yeah. So they have two difference for medium and soft soil, SD and SE soil type. Okay, this is the checking and the displacement. Yes, have a quite low displacement. Yeah, around maybe more lower than 50 millimeter. Yeah. And also in bridge, we have also the high-speed rail well, also using installation system, but not all part. The maybe well, if I'm not the Bandung side part, yeah, using seismic installation system, which is the friction pendulum system. And also, yeah, for design, basically using Chinese standard because consultant is from Chinese, but we check using the ASTOL standard and SNI. So we check using the 100 written period for SNI to 830 and ASTOL GSID. So this is the checking and the properties of the friction pendulum system of the for bridge of high-speed railway. Okay, and then for the last part, yeah, I just highlight some what we do in our campus that we do some research for optimizing and designing base isolation, yeah, for cost optimizing, and also we set for seismic retrofit building and also optimizing, like mentioned before. Is it possible to reducing structural detailing design requirement using, but we still focus on the existing building because when we check, for example, when we want to retrofit the existing building, the detailing of course not comply with the new code, yeah, new building, of course. So, but we should check is it performance is okay. And also the application of on various stuff like irregular, like hail, in hillside, like something like that, and also the satellite hypothesis system. I think that's all my presentation. Thank you.
Thank you. Thank you, Pak Aris, for your presentation. What a very comprehensive presentation. The very comprehensive presentation that covering not only the basic concept of base isolation, but also Indonesian design code and its practice in Indonesia. I think from Pak Aris' presentation, we can see that Indonesian code has a specific section in designing base isolated structure, not only for the building, but also the selection of the ground motion. Okay, for this session, I will open the Q&A session, maybe from the participant offline first. Is there any question? Please raise your hand. Oh, looks like your presentation is very good. Professor Saito want to ask a question.
Thank you for nice presentation. My question is, how do you explain to public people about base isolation techniques? You are teaching at the university, right? Do you lecture about seismic isolation to the students?
Okay, thank you very much for that, Seito. In our campus, basically, we don't teach the specific lecture about the seismic isolation, but we teach dynamic structure. So, yeah, in those part, yeah, we explain some feature to dissipate the seismic force, like seismic isolation, damping, and so on. Yeah. So how those system, yeah, mostly the concept, how the concept the basic equation, something like that. Yeah, we explained it, but not in detail how design the seismic installation. So that's, do you have a class for seismic? No, yeah. Yeah. I think like that. Unfortunately, we don't have a specific class for ini. Maybe later we open a new class for seismic system. Okay, thank you.
Well, in Japan, I'm teaching at the university. Also, well, to understand seismic isolation, we must explain dynamic analysis of the building. It is not so easy. But sometimes we organize, we explain the student using very simple model. One is a conventional fixed model. Another one is a model with rubber at the bottom, and to explain how isolation building works. So student is very happy, and even we explain this kind of explanation to public people sometimes. So people would like to adopt isolation technique for houses or condominium, buildings. So to disseminate isolation techniques, it is important to explain by using plain language to the public people.
Okay, yeah, I think it's a good idea if you have some simulation on the like a small simulation about how base isolation performs. And also when I go to Japan in
you also
yeah, in Shimizu, yeah. Shimizu, yeah. Yeah, we also experience yeah, in Shimizu Institute of Technology, yeah. They also have a checking table that we can sit on that and experience the checking long period, short periods. I think, yeah, it is good. But in our, yeah, in our lab facility, we still not have a checking table right now for those simulation. I think, yeah, maybe it's a good idea.
Yeah.
Maybe later I will, we
In the
will.
future, we can collaborate how
Okay.
to, yeah.
Please, thank you.
Okay, thank you very much.
Yeah.
Okay, is there any other question from the offline participant? If not, let me check. Is there any from the online participant? Okay, also no question. Then let me ask you, Pak. So we have a longer Q&A session. If I can you explain like if an engineer want to start designing a base isolation building, what step that they need to take, like just conceptual to give the participant understanding how to implement our code.
Yeah, this is my opinion. Yeah, maybe right, maybe wrong. Yeah, maybe firstly, engineers should understand what the base atau seismic isolation can change the response of the structures. Yeah, because maybe not all building, like I mentioned, yeah, not all building is suitable using those system. Maybe yeah, like high rise. Yeah. JSI also mentioned, yeah, for high-res, they have some another, but it's very advanced, I think. But the first, the students should understand what the seismic isolation can change the response and which the base structure that can use it. And the second, of course, yeah, they should understand the procedure of the designing. Yeah. Yeah, different country have different procedure, of course, but yeah, in Indonesia, we use SNI. Maybe we can adopted from SE. Yeah, we should understand first the procedure, of course, because in the procedure, yeah, we know that which part that we should design. As mentioned before, like upper part structure, below the seismic isolation, there's different load. Yeah, because yeah, we have expect different response of course. Yeah. I think and also yeah, students should also maybe uh, learn about the product or the assessment insurance because different system have different behavior. Yeah, like rubber bearing or natural rubber bearing, high damping rubber bearing is different uh, behavior and the response of system. I think there's also in Japan there's many types of course like CLB cross linear them is have a difference and then yeah after we understand that we also should how to model in the structural analysis, yeah, because when we design the building or the bridge using structural model, yeah, we should understand how to model it, how to model seismic acceleration, and how to check the element and so on. I think this. Okay. Thank you.
Thank you for the great explanation, Pak Aris. Last, is there any question from the offline or online participant? If not, please give Pak Aris applause once more. The next session is from Pak Felix. Different from another speaker before, Pak Aris represent the manufacturer, different side of the industry. I think he will give us many insight beside of the design part. Pak Felix, time is yours.
Thank you, Pak Eka. So, good afternoon, everyone. Thank you for the time and opportunity given to me to share about our experience in producing and testing the lead rubber bearing itself, the device. So I will focus my presentation on the device of the lead rubber bearing itself. Let me share my presentation. Okay. So in my presentation, it will be divided into 4 different sections. First of all, I will give a brief introduction about our company because we are kind of very specialized company in the very niche market of this bearing and expansion joint. Then I will explain the LRB design for the University Bengkulu Hospital, which is fairly newly completed, but it's still in finishing stage. Then I will also talk about the production, the testing, installation of the LRB. Then we close in that. So a bit about our company. PT Magdatama is a specialized company that supply structural bearing and expansion joints since 1990. And we have been a long-time partner of a company from United States named Watson Bowman Acme. So before we are their exclusive distributor, but since 2015, we are their licensed manufacturer in Indonesia. So we supply our product to bridges and also to building. Here we can see the product line that we supply, expansion joint and also bearings. But I will focus today on lead rubber bearing or LRB as a type of seismic isolator. It's not mine. Wait a minute. Okay, sorry, there's some. Okay. Okay. So we have two manufacturing plants. The first one is in Cikarang area. Well, it focused on expansion joint production. And the second plant is in Kerawang area. It's focused on seismic isolator bearings and also conventional bearings for bridges and buildings. So here are our bearings product. On the left, we can see the lead rubber bearing. And on the right, we can see pot bearing, elastomeric bearing pad, and spherical bearing that typically used for bridges. So our factory is equipped with a complete laboratory to test all kind of material for the bearing, mainly for the rubber, and also some we can also test for steel. So we have all kind of machinery or instrument like UTM, ozone chamber, aging of rheometer. It's a complete laboratory because it's required by our licensor to have a complete testing laboratory. So we are sure that we can produce up to the standard of international standard. Our factory also equipped with the dynamic testing machine to test the LRB in the full scale after we produce. So we can perform the type tests and the factory production control tests, of course. The vertical load capacity is up to 25,000 kilonewton. The allowable test for the horizontal load now we limit at 2,200 kilonewton. For static and for dynamic is 2,000 kilonewton. Actually, it has a little bit bigger capacity, but we limit for daily usage. The stroke is up to plus minus 600 millimeter, and it can move with maximum speed up to 1 meter per second. Besides the dynamic testing machine, we also have two thermal chamber. The hot one can go up to 60 degree, and the cold one can go down to minus 20. This is to precondition the LRB before testing, because EN 15129 and also some other international standard require the bearing to be preconditioned in a certain temperature for the temperature dependence test. Here are some record of past tests. On the top right is our largest produced LRB is 1 meter, 1.09 meter in diameter, and the height is 330 millimeter. It is supplied for 1 bridges in North Sumatra. So our product has been verified. The type test result is has been verified by Bina Marga, and this is the acceptance letter for several projects. And also we have the local content value that is usually required by projects now, and our LRB is up to 78.75% local content value. So that's a brief introduction about our company. Now I will discuss and share our experience about the LRB design for University Bengkulu Hospital. So this is a picture that I get from the internet for the 3D image of the hospital itself. If we can see here in the lower part, there are a picture, an image that the building actually consists of several smaller building, and on the right side, we call building D. This is the building that is isolated by the base isolation. So general information on the building, it's located in Bengkulu, which is the west part of Sumatra Island, which is a seismic active area. The soil, from information that we got, is a medium soil, is SD, and this building will house emergency room, surgery room, ICU, and other critical installation. I think that's the reason why this building is designed with best isolation, so it can maintain operational fully operational right after earthquake event. This is the layout of the building and the base isolation. As we can see on the right side here, there are two lines that indicating that the building, this D building is separated to the building next to it to give some room for displacement. So in this layout, we can see that there are three types of LRB required for this building. Type 1 is shown by the blue dots, type 2 by the green dots, and type 3 by the brown dots. In total, there are 32 pieces of LRB required for this building. Okay, this is the data that we receive for the LRB itself, vertical loads, and the characteristic of the base isolator itself, which has been selected as the LRB. For each type, we have upper bound and lower bound for each characteristic. So we need to calculate the nominal value that we will use as a base of our design for the LRB itself. As we can see on the left, I put some arrow on several characteristic and data that is mainly we use for designing this LRB. So vertical loads, of course, is very important. Also, the second stiffness and characteristic strength will be, will produce the effective stiffness, and also the effective damping, maximum displacement, and total maximum displacement is are a very important characteristic that we consider during our design of the LRB. So a little refresh about the LRB from what Pak Haris has explained before. So lead rubber bearing consists of alternating, actually it consists of rubber bearings and lead core. The rubber bearing parts consists of alternating layer of rubber and steel plate that are vulcanized together to become one bonded part. Then after that, the lead core is inserted in the middle. So when we vulcanize the rubber bearing, there are already holes in the middle of it. So later on, we put the lead core inside. This lead core contributes to pre-yield horizontal stiffness, or we call the QD or F0, some standards say that, and also to energy dissipation. So in LRB, what dissipate the energy mainly is the lead core. For the rubber, it gives a post-yield horizontal stiffness and also recentering capability. So the spring function comes from the rubber. The equivalent viscous damping can be designed to up to 30% or more. Some can be up to 35% also. Now, the design, production, and testing follow EN 15129 code and our best practice. The big part of the standard is about the test, because we must be able to show that the LRB that we design perform as what is needed by the building. So the characteristic is very important. There are type testing, which is dynamic, and we consider it destructive. 2 pieces minimum must be tested. Then after that, cannot use that in the construction. Then there are also factory production control tests that we will sampling from the test LRB, from the product of LRB that will be supplied to the project. So this is just some general LRB characteristic equation. We can see from the hysteresis loop, the stiffness, the horizontal stiffness, which is called KD, or in some other standard, maybe set KR or K2, and the characteristic strength is F0 or QD, which is the horizontal load of the hysteresis loop at 0 displacement. This is contributed by the lead core, and there is effective stiffness, design displacement, and maximum displacement. And on the right, there are some expression or equation for the characteristic of the LRB, such as the horizontal stiffness, which is the product of the effective stiffness, which is the product of horizontal stiffness and also the characteristic strength divided by the design displacement. The horizontal stiffness of the rubber itself is a product of the shear modulus of the rubber, the area of the rubber bonded to the steel, divided by the total height of the rubber. Only the total height of the rubber without the steel, because what contribute to the displacement movement is just the rubber. The steel laminae or the steel shim inside the rubber is what provide vertical stiffness. So, and this is some other formula. This is also another other equation for calculating the stiffness and damping from the lead core itself, the shape factor, the reduced area of the isolator. So we use this in the design of the LRB. And we also do many checks based on the EN 15129 rules. So we need to check the strain of the rubber due to the compressive load, due to the angular rotation, due to the translatory movement or displacement, both in ultimate case static and ultimate case also seismic. Then we check also the reinforcing plates. Then more checking will be the buckling stability. We must make sure that the LRB will not buckle during big displacement. Also rotation limitation, tensile of the rubber, and some other calculation. So I just show you some of the equation. Basically, we need to calculate all of this checking, and we need to make several calculation iteration to get the most efficient LRB design. So once we get the efficient LRB design, then we can submit it to the project. So after several iteration for the calculation for this project, we come out with 3 design, because there are 3 types. For the type 1 or LRB1, its diameter at 150 and the height is 277 millimeter. And the type 2 is diameter 700 by 257 height. And type 3 is 600 millimeter diameter and the height is 273. So now we have 3 design LRB. And there are 3 different sizes of LRB. If we design them independently, we may need to do 3 type testing. So each type test require 2 pieces of LRB. So if we design them independently, we need to test 6 pieces. But fortunately, there is a rule in EN 15129, what we called about a similarity rule. So where it says if one LRB is similar to the other one, or the difference is within the checking of that standard clause, then we can consider only one of them to be tested. And that's what the case for the LRB for University Bengkulu Hospital. We designed the LRB number 2 and number 3 to be similar to the number 1, which is the biggest one. This is the similarity rule according to EN 15129. It says that the new type test shall be carried out if different elastomer compound is used. So to be able to have only one type test, then all the 3 LRB is designed and produced using the same elastomer compound, same material, which is natural rubber, and also same shear modulus. Usually shear modulus is the key characteristic, inherent characteristic of the rubber material that is selected for the LRB. And the other rule also, we keep everything in check, such as, for example, decrease any external dimension of the isolator compared to the one tested cannot be less than 50%. And we know from the design before, the minimum, the smallest one is 600, the biggest one is 850. So it's more than 50%. And we check everything, and we summarize. So we prove that our design for the LRB2 and LRB3 is similar to the LRB1. Then we submit this similarity check together with all our design. So then we can test only in type 1, already fulfill the other 2 types. The type 1 is selected because it's the largest size, diameter at 150. So now our design is already approved. Then we can start the production of 2 pieces LRB for the type testing. So here are some raw material that we use, or our local material, the high strength steel, natural rubber, flat core are local material with some high local content value. All raw material must be checked against the quality of the specification. For example, on the left is the spectrometer test for the lead core. It must be 99.9% minimum purity of the lead core. The steel, the tensile strength, everything is checked. And on the right is our test for the rubber. So we always test for the rubber internally every time we produce, but we also do comparative testing result to the independent laboratory. Usually we test in rubber laboratory in Bogor. A bit information about our product. We improve our formulation for the natural rubber to have high ozone resistance equals to the chloroprene requirement. So natural rubber only required to have ozone resistant up to 25 part per 100 million, while chloroprene in EN standard is required up to 100 part per 100 million. So it's 4 times higher in terms of, we can say, ozone resistant, because the test require much stringent requirement. But our natural rubber is already improved. So our ozone resistance is equal with the chloroprene rubber or synthetic rubber. Then in doing so, we hope that the lifetime is can reach what is targeted by the design, I mean the EN standard, which is stated in the specification to be 60 years. This is the general flow process, the production of LRB. All the process is done at our own factory, starting from the cutting of the plates until the mixing of rubber and until the testing. So this is some general processing photo of the steel plate. Like the steel plate is cut with laser for the thin steel plate. Then we machine the thick steel plate, we blast, and we apply the adhesive on the steel plate to bond with the rubber. So our adhesive application is we take great care in that process, because the life of the LRB is very depend on the adhesion between the rubber and the steel. And this system is automated roller and oven system. Also for the rubber material processing, we start with the computerized automated weighing. We mixing everything inside the factory. After finished mixing, we always check every batch. So 100% of the produce, the mixed rubber is tested first. If everything is okay, then we continue with vulcanization with the steel plate. So this is our vulcanization machine. And on the right side is the finished LRB1. We can see there are already holes for the lead core. Then after we put the lead core, we do finishing. Then we start, we can start with the type test for the type 1 LRB for this University Bengkulu Hospital. So for the type testing, 2 pieces must be tested. So this is the requirement of EN. First, we need to do the type test, 2 pieces of LRB, and we need to do at a high speed dynamic condition, which simulate the seismic requirements, seismic condition. And there are 7 categories of the tests. The category number 2 to number 5 are cyclic tests at 0.5 hertz. So it's 2-second period to complete 1 sine wave of a motion. And the last 2 tests, which are shown as red, we consider that as, how to say, destructive tests because it tests the LRB beyond the design capacity, beyond the design load and the design displacement, and it must not fail. If we already finish the type test and everything, the result checks, then we can do the production of the LRB. After the production of the LRB, the mass production, then we need to select the LRB randomly for factory production control. EN 15129 dictates minimum 20% from the total produced quantity to be tested. But because the Bina Marga standard, which already adopted EN 15129 for bridges at 10% more, so minimum 30%. For this project, the University Bengkulu Hospital also follow the 30%. So the test for the factory production control, only 2 tests, which is the compression stiffness and horizontal characteristic. It's a cyclic test, but it's not as fast as the requirement of type test. It is only 0.1 hertz. So this is the protocol test for the type testing. There are total 18 test run because in the 7 group, some group there are require many tests. The first test is we check the compression stiffness. There is no pass or not pass value. We just measure and it become a reference value for the factory production control test. But we also need to check the visual of the LRB because this is the first test. So if everything is okay, no bonding failure, all reinforcing plates are aligned, there is no surface crack, then the next test can be started. The test group number 2 is the horizontal stiffness, where we really measure the horizontal characteristics of the LRB itself. How is the stiffness and how is the damping? So according to EN, we do the test based on the displacement according to the shear strain of the rubber. So we need to calculate the movement, the displacement based on the percentage of the height of the rubber. So in this type 1, the height of the rubber is 137 millimeter. And the displacement design during seismic is 222 millimeter. So when we calculate that, it's 162.1% of the rubber height. Therefore, we need to do 2 tests, one below the 162, which is 150, and one above, which is 200%. So in this test, we will get the effective stiffness and effective damping from the LRB itself, but only from the 3rd cycle. That is what is counted. And from the 150% and 200% result of the effective stiffness and damping, we will make an interpolation to find what is the effective stiffness and damping at 162%, which is the design displacement of this LRB. And that value must be compared to the design value that is needed by the building. and it must be within plus minus 20% from the design value. But if we check the upper bound and the lower bound given before against the nominal value, actually it's larger than 20%. So I check it's like upper bound to lower bound from the middle is 22%. So by having this 20%, it's already more safe. So we will not exceed the upper or lower bound. So here is some footage video of the test. This is the fastest test, which is the 200% strain. Maybe it's a bit lag. I will try to replay it. Maybe it's better. Yeah, still a bit laggy. But basically, we test the LRB at 0.5 hertz. So that's 2-second period, plus minus 273 millimeter with peak speed is 858 millimeter per second. During the test, the resulted hysteresis loop can directly be seen in our lab, and usually the independent expert witness team will directly calculate the stiffness and the damping by estimation. So that's group test number 2. Now, group test, the next group test is, we call it frequency dependence, where we test the LRB at a frequency lower than 0.5 and higher than 0.5. The lower one is 0.1, the higher one is 1 hertz. So it's very fast because 1 hertz meaning the period is 1 second. The purpose of this test is to see how is the characteristic of the LRB is stable when a real seismic happen and the frequency is not 0.5. Maybe a bit more, maybe a bit less. Usually it should be a bit less than 0.5. But this is to see how stable it is. And the acceptance criteria is the effective stiffness and damping at 0.1 and 1.0 must be within plus minus 20% from the middle frequency, which is the 0.5. This is the video for 1 hertz test, but maybe it will not run smooth via Zoom. But this is 3 cycle at 100% strain displacement of the rubber, and it's done at 1 hertz. The next group test after the frequency dependent will be the temperature dependence. We need to check the stability of the LRB characteristic when the temperature varies, maybe a bit colder, maybe a bit hot, than the room temperature or the middle temperature. So the upper temperature is 40 according to EN standard, but the lower temperature here is 10 degree, follows the Bina Marga adopted EN that has been how to say improved. 10 is the lower surface temperature. So we condition the LRB minimum 12 hours on that temperature before we take out and we do another test. And the acceptance criteria is plus minus 20% from the middle for the high temperature, and for the low temperature, it has a wider acceptance criteria up to plus 80%, but only minus 20% allowed. The next group test is repeated cycling. So all tests before for cycling only 3 cycle, but this one is 10 cycle to see how it will be stable when there is a longer, how to say, seismic movement happen. So if we see here, so this is 10 cycle, but maybe it's a bit laggy, the video. So this is the most cycle test according to EN requirement for the type test is 10 cycle. Then we can see from the fourth or fifth cycle to the 10th cycle, it's very close to each other. There are some reduction, but it's also it's already can be say quite stable because it's very close to one another. Now, after we finish the cyclic test, we come to the destructive test, the compression capacity. We need to compress all the RRB that has been tested cyclic for many cycle up to 130% of the ultimate static load. So it's 1.3 times, and we check there must be no bonding failure or other imperfection. The last one, this is the video that we fast forward 25 times. So at the beginning, the LRB is still smooth, but when we apply the pressure, we can see the bulging of the rubber, each rubber layer. So the bulging of the rubber layer is normal, but it must be equal or almost equal from one layer to the other. Then we can see the bonding is still good. That's the meaning. Oops. Wait a minute. The last test, which is another destructive test, is the lateral capacity, where we displace the LRB 1.15 times from the maximum design displacement. So again, it's already beyond the design, and it must not show any failure, such as bonding failure, surface cracks. 2 millimeter, it's the minimum, the requirement. So if there is any crack or 2 millimeter long or deep, and it failed. So yeah, that's the criteria. And no permanent deformation on steel members in this test. So after the test, it should come back to the original dimension and situation. So after all the tests, then we take out the bearing to get checked the condition. Must make sure there is no crack or any imperfection. Then if everything is okay, then the type test is done. So this is the test result that we have for the type 1 LRB. We can see the effective stiffness deviation for unit 1 is minus 2.14%, meaning the effective stiffness that we get from the test is minus 2.14% compared to the value the nominal design value that is given before. And the damping deviation is minus 2.39%. The second unit is minus 4.19, and the damping is plus 1.22%. So it's very small. So for this one, is we got very small deviation, and it should be very good in the range of upper and lower bound, should be somewhere in the middle. Now, after this test result approved, then we can do the production for the LRB, the 32 pieces. After that finish, then we need to do the FPC test. This is the footage photo from the FPC test. Two tests that need to be done is the compression stiffness, and one is the cyclic, the movement up to design displacement, but the frequency is 0.1 hertz only, so not so fast. After the test, everything is checked. So all the selected LRB, the 30% is pass the FPC test. Then after the test, we usually do the touch-up because some friction with the test machine or the plate can scratch the paint. Then we will do the touch-up before we send to the project. Now, after we send to the project, we do the installation also for the LRB. So here are some photo of the pedestal that will be hold the LRB. So we check the flatness with this is a mirror. So to make sure, no, the glass sheet to make sure it's really flat. Then we place the LRB inside. So we make sure all the LRB level is good. Then the contractor start to put the rebar for the column on top of it, and also the formwork to protect the LRB. So on the right side is after finish, we grout the lower anchor bar of the LRB. Then the installation is finished. So this is the finished condition now. So this as a closing summary for my presentation. A minute. Okay, so for the LRB for the University Bengkulu Hospital were designed, produced, and tested in Indonesia, complying to EN 15129 requirement, with team of independent expert to witness and verify the test result. So now the LRB has been installed, and the building is expected to be safe and maintained operational or fully operational after seismic events. So that concludes my presentation. Thank you for the time and opportunity.
Thank you very much, Pak Felix. I think it's very insightful. We can see a different testing protocol using EN. I believe SNE 1726 also have its testing protocol. Maybe a little bit different, but it also have a clause for a similar size isolator and production test. But maybe in SNI, the requirement is 100% production, a little bit higher. But I think it's a good insight. Okay, now I want to open the Q&A session. Maybe for the offline participant first. If you have any question, you can raise your hand. Okay, Hoto-san.
Thank you for the good presentation.
Thank you.
I would like to ask about the device properties. So let's imagine some engineer want to start the design of the base isolation buildings. The device property is the first requirement engineer want to know. So in such a case, can engineer can be provide some device property from your side, or engineer should provide any single property to your side?
Okay, thank you for the good question. We can help the engineer to design by giving how to say starting point of the properties. So we give the stiffness and maybe the damping, so the engineers can input that into their model and to see whether it's good enough for their target. If not, then we can certainly works with the engineer to find more solution. So we have done it before. So yes, we can support that.
So from inside you have some proper setup.
Yeah.
Oh, okay.
Yes.
Thank you.
Okay. Welcome.
Is there any more question from participant offline? If no, can we check to the online participant? Is there any question? Okay, there's one question. Okay, maybe the online first. Can you show it on the screen? Okay, it's come from Mitria Widyaning Tias. The question is, under what conditions should SDR high damping rubber bearing be used instead of lead rubber bearing?
So high damping rubber bearing, as we can see from Paris' presentation before, normally has damping between 15 to 25. More commonly is below 20, so it's less damping. Less damping, meaning more displacement if the input is the same. So it really depends if we can see any benefit of the using the HDRB. The displacement, more of the displacement will need to use bigger expansion joint, and also for the other installation like the piping and the cable must need to consider that. So normally we I think in the last to say 10 years is almost LRB is chosen in projects in Indonesia from what I experienced. So high damping rubber bearing has some benefit also because it's all are rubber. So I think the minimum how to say the minimum force to start movement of the isolator is less compared to LRB, because LRB has lead core. Then we need go over that yield force to be able to get the damping. So maybe if the seismic is not so big, the area, the zone is not so big, maybe HDRB can be considered also. That's my opinion.
Thank you, Pak. I think I visit your factory yesterday, and you mentioned Magdatama also can produce SDRB.
Yes.
May I know the damping ratio you can produce?
15%.
Oh, 15.
15%.
Thank you. Pak Aris, do you have anything to add? Okay. Maybe I see we have offline participant want to have a question. Oh, okay.
Yeah, please.
Thank you for the opportunity. I want to ask about the cost. Is it possible for the LRB or your product or any other seismic isolation product can have lower cost, and that is for the product? And for Mr. Aris, is it possible to design the building as a system with the base isolation, but it has a lower cost, so it will be feasible? Because in Indonesia, probably the cost is the main barrier to be applied in many buildings. That's all. Thank you.
I think I remember from the morning presentation by Professor Saito, it's also in Japan is cost is number one factor. So same in Indonesia, cost is also the how to say the barrier in application of this seismic isolation. But usually it's I will say it's less than 3% maybe of the building cost, maybe. But if it's very tall building, maybe much less than that. But so how to make it more less cost? I think now it's already less cost for us. So I think for how to make it less cost, what we can do as a manufacturer is we design it as efficient as possible. We have the capability to produce many kinds of rubber compound shear modulus. And in the case of the University Bengkulu Hospital, we already select the shear modulus that is the most efficient one, meaning the size and the height is already optimized. If we use for example, a very hard compound, then we need a very tall LRB. Also, maybe the diameter cannot be that small because of the stability issue. If we use very soft compound, then maybe it can be shorter, but the diameter will be larger. So in that regard, how to make it less in cost value, the manufacturer must be able to tailor this material of rubber so we can get the most optimum design like what we did before. So I think that's my answer for that.
Okay, thank you. If I'm not if I'm not mistaken, you mentioned that how to reduce the cost for building. How to reduce? Okay. Yeah. The design of because I mentioned before that in design sometimes when we use seismic isolation we can reduce the seismic forces. But some cases because the R is 2. Sometimes the seismic force, if you use, for example, a special seismic resistance system, SRMF, we have R8. But for seismic isolation R2. With the same level of seismic. So even we reduce the seismic force due to the damping and also the period switching, but sometimes still maybe same or so the main target for seismic isolation mostly performance, because after seismic earthquake happens, we no need to repair. Maybe that's the main point. For reducing the cost of the isolator, one type is like Magdatama. They produce locally, use material locally, and also testing independently by Magdatama. So I think before we should import the material, we should testing all and other countries. Of course, they will be increase the cost. So by increasing the TKD, I think also reduce the cost. I think. What else? The second thing is I think how to design optimizing. I think it's also important. So we should design optimizing the using of the isolator, the number, because as he mentioned, Mr. Felix mentioned, if we have many types of isolator, for example, we have tested each of that. But he clever, he used and similarity, so not the test over. So something like that. So we can, reducing the type, for example, and also, like hymns using similarity, but still acceptable by code. I think also may reduce the testing costs because testing costs I think also expensive. I think.
Yes.
So I think that's the way we can reduce the cost using the seismic isolation. Maybe also, we should develop our seismic isolation, but it needs times and cost also. For example, for low-rise building like maybe 2-res, maybe if you use the product, maybe it's too expensive. Maybe if we develop our seismic isolation system with low cost material and new system with low cost, I think we can also reduce. I think that's all for me.
Okay, thank you, Pak Aris, Pak Felix. Is there any question? Okay, Professor Saito.
I in my presentation, I explained about the fatigue and creep problem of lead rubber bearing under wind load. I want to hear your opinion about this.
Okay, so for the creep and fatigue, in the EN standard, there is a requirement for test for creep, but it is directed to high damping rubber bearing. So in the creep test section, if the damping is less than 6%, if I'm not wrong, if I remember correctly, then we do not need to test the creep for the natural rubber in according to EN. And if the another criteria, if the rubber is not natural rubber or not chloroprene rubber, then we need to test the creep. So following that standard, we are not required to test for the creep. Maybe the standard stated that for the natural rubber, I mean, we can deduce from what the standard says that natural rubber maybe have a good creep characteristic. So we are not required to test that. But we do require to test one test called slow crack growth, which is the growth of the crack for the rubber by tearing a bit the rubber and suspend some weight over 24 hours to check whether there is a propagation of crack. So that is what's required. For the fatigue test, there is one requirement to do cyclic tests like this for 2 million cycle, but that is only applied for bridges. So it says in the code is for bridges. Fatigue test may be required following EN 1337-3, and it's a 2 million cycle loading. So it's from, if I correctly, is 25 MPa, then the low loading is 8 MPa, 25 MPa to 8 MPa is for 2 million. And we must check the vertical stiffness before and after the fatigue test. It must not increase by certain percentage. So that's what I can share, Professor Santo.
Yeah, maybe you are talking about rubber material.
Yes,
but
yes.
I'm talking about metal material, I mean lead.
Oh,
And
lead.
it may go enter nonlinear in case of strong wind, like a typhoon.
Yep.
And because of the fluctuation of wind, lead material repeat hysteresis many times.
Yes.
And it will cause fatigue problem. And it's a very new issue even in Japan.
Okay.
So probably in the future, same problem may happen here in Indonesia. And one more comment is, Japan, it is very common to adopt natural rubber bearing plus oil damper for damping. Because natural rubber, it's a linear.
Yes.
No worry about the fatigue.
Yes.
And oil damper, no worry about fatigue also. After repetition many times, as long as oil is no liquid, I mean
leakage.
Leakage. We can expect the same hysteresis many times. So probably this is one reason Japan recently adopted natural rubber and oil damper combination.
Okay.
Yeah, this is my comment.
Okay. Thank you so much for your insight. I think it's a interesting hybrid system that we see from the presentation before. Then maybe it can be also applied in the future. Yeah. Maybe a little a comment also from the previous presentation. I saw that there are a test for the bearing up to 100 cycle, 200 cycle, up to 500 cycle. So I think it's a good idea for us to try to test that also, because the standard only dictates maximum 10 cycle. But I'm also curious to see how it will perform if we do up to 500 cycle. Maybe we cannot do dynamically 0.5 hertz because our machine capacity is not that up to that big. But we maybe can do the quasi-static test up to 500 cycle will be very, very interesting. And I would like to do that soon. Thank you.
Okay, thank you, Prof. Saito. Is there any additional question from the offline or online? Okay, we have online question. Okay, the question is from Balai Keamanan Jembatan dan Terowongan to Pak Felix. The Besuk Kobuan Bridge is Java use LRB. How was the LRB evaluated during the recent eruption of Mount Semeru, especially its durability against maximum temperature and acidity of the volcano lava?
Okay, very good question. So we joined the online meeting last week about this bridge. Yes, there was it called cold lava, but actually it's still hot. It's still several hundred degree temperature. So the next week, I think we will go to the Besuk Kobokan Bridge with the team from Bina Marga to check the bridge, and also we want to check about the LRB. From the photo, we cannot really judge the condition because it's very dusty. But if the temperature there it's still within the limit, it should be okay. Hopefully, it should be okay. The upper surface temperature is only 40 Celsius degree for the LRB. That is what we use for the design and during the testing. But the natural rubber bearing should be able to resist up to 70 Celsius degree in the bearing itself, because we do test the aging up to 70 Celsius degree. But the longer it stays at high temperature, the aging will become faster. So maybe some lifetime will be faster, become harder, the rubber. So we are also looking forward to the site visit next week to that bridge. And hopefully our team can go down to see the LRB that we have supplied and installed. It's just that we informed before, the access down there is not that easy because it's down in the bridge. So we will know next week about the for the Besukobokan, and I hope it's okay.
Okay, thank you. So there's also possibility you will extract the sample to be tested in the lab.
That's what one of the question during the meeting. So how to make sure it's still okay? And if you really want to make sure the bearing, then you extract it out, then bring to our factory, then we can test, no problem. But it will not be that easy because the bridge must be supported by other LRB. So then some people said, okay, better we buy new one. So we will try to check the condition, and also we will check one properties is the durometer hardness for the rubber. If it increased too much, or if there is a sudden drop and becomes soft, maybe there is some window time that it exposed to very high temperature. We hope it's not the case, but we can see in detail next week.
Okay, a very interesting case. Is any additional question? Oh, this from Gambiro to Pak Felix. There's 3 questions. The first is the material used natural rubber or synthetic rubber? The second is how durable this LRB and its fire resistant property, and how to replace existing bearing in a building.
Okay. The material used, what we use is natural rubber. So 100% natural rubber. And we use, we call it SIR, Standard Indonesian Rubber. So it's natural rubber. But maybe my presentation before is a bit not clear. What we do is the compounding, the chemical we use, we use a good chemical that we can improve the ozone resistant equal to the synthetic rubber of chloroprene. So the material is natural rubber. Second question is how durable is the LRB? It should be very durable, and the target is 60 years lifetime according to UN standard. That's we already do some tests according to EN standard. small sample, and we also have aging the full scale of LRB for the aging time and the temperature target by the EN. And we see that the properties it does not change a lot. I mean, just change just a little. It become harder for the rubber, but not that much. How resistant is it to fire? Natural rubber is burnable or combustible. It can be burned. So I would say it's not that good to resistant for fire. But if a fire resistant is needed for the rubber bearing, usually there is a cover around it that we can provide to give some more resistant to fire. Yeah. Maybe few hours of fire. That is possible. How to replace HDRB or LRB in the building? I will say it is replaceable, but not that easy. If it's a bridge, we can jack, but for building, it's not possible. It's very hard. From what I know, one of the possibility is we put some temporary how to say structure between the below the LRB and the column above it, transfer the load with the some hydraulic system. Then we may demolish the pedestal so we can take out the LRB and install the new one. So it's not an easy or a fast job, but it can be done. That's why the lifetime of the LRB and all the tests is really needed to make sure it's long lifetime.
Thank you. If allowed to add a little for the number 3 question, as a structural engineer, replacing SDRB, LRB is something that's very possible. And in some cases, the engineer or the client already prepared the possibility to it. So
yes,
during the design, they already designed the jack point, and also the LRB or SDRB have a special feature. They have double plat usually, the embedded plat and the plat that connected to the bearing. So when you open the bolt, you can extract it easily. But it should be during design stages, no, not after. So it's prepared in the front.
Yes. So in theory, even we do not use the double plate, it should not stick because we as we can see before from my picture, the pedestal has been set. So we just put the LRB on top of it. Only the dowel is grout. So in theory, if we open the bolt, then we can slide it out.
Yeah.
But maybe after several years, maybe it's not that easy to take it out.
Okay. Is there any additional question from offline or online? Okay. So from Pak Gambiro, in a building there are various type of base isolator. How do you choose the type of to use? Is for Pak Aris.
Okay, thank you. Yeah. As I mentioned before, each type of base isolator have its characteristic. Yeah. So yeah, basically it's free to use any types of isolation. Yeah, depends on what we expect to behave. I think. Yeah, for example, if we want higher stiffness or higher damping, we can use, for example, LRB, but still can change. For example, we can combine with the natural rubber with low damping, but we added the dampers. So I think there's many possibilities. It depends on our choice, what we expected the structure to be performed. And yeah, mostly in Indonesia is about the cost and also about the availability of the devices. Sometimes like dampers is still difficult in Indonesia, yeah, to get dampers or with also so maybe it's will be more expensive. So yeah, yeah, as a designer, we should think which our best choice that we have and what we expected the performance. So we choose that types of accelerator. I think this.
Thank you, Pak Aris. Is there any more question? Oh, there's still because we okay because we only have two speakers, so we can answer more question. Okay, the question is from AW to Pak Felix. For buildings that have enough space to other building around them, seismic isolation provide answer. But the majority building in Jakarta or Indonesia generally has no space at all to other buildings. Mostly they stand so tightly. What if will happen if your building has applied seismic isolation, but your left, right, and rear building have not applied it? How do you regulate this in the code? How do you analyze this? Thank you.
So I will try to answer this from what I know. You see, seismic isolation always generate displacement. So if it's very tight and it's not possible to have a how to say space for the displacement. If we use the seismic isolation, it maybe before the displacement is reached maximum, it's already hit another building. That will be catastrophic. It will be dangerous, I think. So I think it need to assess if the condition is not possible, whether seismic isolation is the right choice for dissipating the seismic energy. In the morning session, we see many option in Japan. So maybe another other system will be more suitable in that case. So maybe that's what I can share, because seismic isolation always give displacement. Um, Maybe we can also check whether the kind of stiff, how to say, seismic isolation, for example, if it's LRB, then we have high characteristic strength, will still give benefit or not. But maybe not so much benefit in that case. So maybe it's more for not for the device itself, but more for the surrounding and how applicable is this in that building. Maybe that's what I can share.
Okay, thank you, Pak Felix. I also think the same because base isolation building is dissipate energy through movement. If it
Yes.
cannot move, it's not base isolated building. Okay, maybe we have last question. Is any last question from online or from offline? Okay, I think we'll take this as the last question from Pak Akbar to Pak Felix. Do you mind explain the process of installing the LRB in the Bengkulu building? And is there any issue about the position LRB on the structure, and also how to make sure the connection of LRB to the element structure building established?
So can I share my screen again?
Okay.
Is it possible? Let me share. So wait a minute. Wait a bit for the slide. Okay, so the position of the LRB has been determined in the design of the building. So we don't choose as a supplier for the LRB. We do not choose where is the position. So we already follow the predetermined position by the designer and contractor. The contractor are the one who made the pedestal. We are the one who do the finishing and to make sure that it's flat for our LRB to sit on it. So I believe the contractor has done a good job to positioning the point for the structure where the LRB will sit on it. So here is the position and how to connect to the structure. On the right, we see that the LRB has anchor bars. So that is the connection to the lower structure and the upper structure. So these anchor bars will get inside the pedestal on the bottom, and on the top, we see the. So on the left bottom picture, we see on the top here, maybe let me zoom in. Uh, in the middle of the rebar, we can see the dowel or the anchor bar of our LRB, which is already, how to say, tightly placed inside the rebar. And once the concrete is poured on top of it, it should be tightly connected with the column. So that is how the LRB is connected to the upper structure and to the lower structure.
Okay, thank you. I think many of the question given to you is should we give to the designer of the building?
Yes, yes.
But thank you for the answer. I think this conclude this afternoon session. Please give applause once more for Pak Alis and Pak Felix. And also please give applause for morning speaker, Professor Saito, Muramatsu-san, Hota-san, and also Sawada-san. Thank you. I will give back the session to the MC.
Okay.
Maybe we can take our leave. Oh, okay. I think they will proceed for the certificate.
Thank you for the amazing presentation from the speakers. The next agenda is a certificate from our head of Subdirectorate of Building and Environmental Infrastructure Reliability. For all the speakers, we would like to invite you. Of the stage. And also the moderators, Mr. Rudy and Mr. Eka. Thank you for Professor Taiki Seito from Toyohashi University of Technology. Thank you for Mr. Akit Sugumura Matsu from Taisei Corporation. Thank you for Mr. Yusuke Hota from Mitsubishi Jiso Design. Thank you for Dr. Eng, Insinyur Aris Arianto, STMT from Institut Teknologi Bandung. Thank you for Mr. Felix Hotama from PT Magdatama Multi Industry. Thank you for Mr. Eka Ciptawiguna, STMTS Moderator. Thank you for Dr. Eng, Rudi Setiaji Agustin Ningtyas, STMN. I would like to invite all participants to have a photo session with the speakers. Distinguished participants, after hearing the sharing knowledge from 5 incredible speakers and 2 amazing moderators, we have now reached the end of our event. It has been a pleasure hosting this event today. Thank you all for your attention and participants. I hope you have found it to be valuable and enjoyable experience. Thank you and good evening. The last agenda is closing by head of Subdirectorate of Building and Environmental Infrastructure Reliable to Mr. Ferry Ekaputra, STMDM. The time is yours.
Okay. Bismillahirrahmanirrahim. Good afternoon, ladies and gentlemen. As we conclude today's workshop on base isolation technology, I would like to express my sincere appreciation to all the participants, speakers, and organizers. Our special thanks go to Japan Society of Seismic Isolation for their strong collaboration. And today's session have reinforced the importance of innovative seismic protection and the value of the international cooperation. The insight share will support our ongoing effort to improve the safety and resilience of our buildings and communities. Let us continue this momentum through practical application, further research, and strengthen partnership. Thank you for your participation, and we look forward to future cooperation. Thank you very much.
Thank you all for your attention and participation. I hope you have found it to be a valuable and enjoyable experience. Thank you. And see you in the next event.